esatto. correct.
The difference between the simple random position is that in games usually the pieces are balanced, so we cannot expect a good game when one of them has, say, 5 more pieces left in the game. So this is a position where there are 225 sides, and of them 71 is black and 70 is white.
It's all right. Oh, I know. Is this the problem? No.
Traditional sequential algorithms, which we find in books on computer algorithms, are like this one. The main 2 variation is as follows. One of them is making a list and selecting randomly elements from the list, and repeat until the sufficient number of elements have been selected. The other is working in bit vectors, tries to find an empty bit position in the set, and if it is empty, then set it to 1, and if not, then tries another position. And it repeats again until the sufficient number of elements has been selected. They both have weaknesses. They are inherently slow. At least k steps are needed for the generation. And in each step, both consumes a full random number. And there is also a problem. The variation 1 has a list of k of n elements, and it is a lot of memory. And second, it has a problem. It is much more economic with memory, but it has a problem with density when the position is densely populated. Then you have to try many other positions while he finds an empty one. And also the second variation executes consumes a random number even in those positions where it rejects finally. And another problem is variation 2. It executes a random number of steps. The variation 1 executes k steps, but variation 2 executes more than k steps usually. So I first, when I didn't find a good algorithm to start with, I proposed my fast algorithm for CPU. That is the following: a bit parallel algorithm to speed up the process and also to economically use the random bits. First is we select we have a subset and a candidate set. The candidate set is the full position initially, and the subset is the empty set initially. Then we select a random set of elements from candidates and count the number of elements in it. If the selected set can be added to the subset, then we add it to it and reject and delete them from the candidates. Delete them from the candidate set. If, however, the selected set cannot be added to the subset without exceeding k, then we knew that the selected set is too large, and in the future it will be enough to select from the selected set, the new selection. So the unselected candidates could be rejected, and we repeat these 2 steps, step to step, until k is achieved. The good thing with it that in any case, the randomness chosen selected set is always on the average half of the candidates. So in each step, we either include half of the candidates as or in average, the procedure stops in about log n steps. And in each step, it comes with one word of random width, so the total of log n words of random widths are selected. Comparing this to the original algorithm, this is a much better, much faster method. And the simple instructions are mostly enough to do it. The only non-basic instruction is the counting of the ones. However, fortunately, today it is not a difficult instruction because both CUDA and CPUs, modern CPUs, have since a decade a population count instruction, which is very fast for this purpose for one word. And now this is the full implementation for CPU or CUDA. We have three sets: the subset, the candidates, and the selected candidates, and a few variables. And here we have initialization. The subset is set to empty, the candidate is set to full set, and the next part is the selection and population count. Here we see the CUDA version, Current and POPSI is how CUDA is solved this problem, the random numbers and the population count. But very similar is the case for CPU solution. Only these two things has to be changed if we change it to CPU. And then the two branches of after a decision, if selected set could be added to can be added to the subset, then we add it and delete it from the candidates. If not, then the candidates will be the selected set. The new candidates will be the selected sets and the reduced candidates. So when we execute this code, it results in a subset containing k elements, where k is arbitrary. We see that k0 is handled by the first. Immediately crashes out here, the k0, so it's very fast, but it is not a frequent use. Simply, we can change the declarations and the name of the functions to use it for 64 bits. However, there is divergence in it because in a CUDA implementations, there is a loop, the while loop, and there is an if conditional statement, and both results in the threads are executing in divergence. The loop divergence is because the algorithm executes a random number of steps, and it depends on the random number sequence. The conditional if divergence is because some of the threads execute the if branch, the others execute the else branch. But the processor or CUDA computer card cannot do this simultaneously. Now let's see what is the measurement of speed of this generation. So in a mid-category board, we achieved 28 billion subsets per second. So it's a very nice result compared to the original algorithms. We measured what is the difference between the single thread execution speed and the multi-thread execution. What is the loss of multi-thread execution compared to idealized single thread execution? We did this, but in each warp we used only one thread so as to avoid any divergence, and we measured the execution time and multiplied it by 32 to scale up to the original size. And we had a hypothetical generation speed of 58 million subsets per second. That means that about 2 is the multi-thread slowdown factor. That is the multi-threading loss, again, compared to the idealized single thread execution. The program, as it is compiled, uses in the critical paths almost exclusively registers. So no memory issues and latency problems is expected in the program. So we expect it to scale a larger card according to the raw computing speed of the card. That means that in a 4090 RTX 4090 card, I expect a speed of 5 times as much as in this mid-category card. So, but this was only for the single word problem, 32 bits standard 7. Now, however, we want to do grids, something like in the game positions I show. But how to store them? The local memory, which is in the large device memory, it is there, but slow. The shared memory is still slower than registers and has limit in size because the register storage is exactly 5 times as big in most CUDA cards than the shared memory. And also shared memory has its addressing program to we have to consider access patterns, and with registers it is much less problem. However, registers have their own problem because they cannot use arrays. There is no way to put an array in a register so that we can programmatically select by index an element. The only case is where the register array is fixed size and access is clear for the compiler at compilation time. So we can use a fixed line registers if we use a very simple for loop, and the compiler rolls it out as if it were scalar variables and solves it with registers. But it is limited. But from the point of speed, and if we can live with this constraint, registers, that is the only viable solution for the real fast implementation. So first is what I call a thread-wise implementation. That is what we've seen. Code is executed in each thread with appropriate modifications to handle the full board instead of only one word. That is one row of the position. So each thread executes. They are all working on different problems. And what we do is threads are replaced by arrays. and all operations are done with 4 loops on these arrays. And one more thing, the element counting, which was a simpler instruction for the single word case, must be summed for all the positions, because we want to have k element in all the positions. So this is the changes. And we see now this CUDA code for thread-wise and full position. The size y is the number of rows, how many rows are in the board position, and each row is a 32-bit word in this implementation. What we see is that it is very similar code to the original one. In some places, here, and here, where we work with the sets, we everywhere put in 4 cycles, mechanically put it in, and the compiler did the rest. One thing, however, was different, because the summation has to be done for all the board, and then it is done here. It is also in this for loop. So we see the code is relatively similar to the CPU with a normal vectorization. And we measure the test of this application, and with 32 by 32 grid, we achieve 1 billion grids, again for arbitrary k from 0 to 1042, because 32 by 32 grids has that number of elements. But we have a storage problem, because we have 3 arrays in a 32 by 32 case. We have 3 arrays, and each needs 32 registers. So these 3 arrays alone need 96 registers. With the rest of the variables, we had 120 registers for the whole grid. Threads can hold in CUDA only 255 registers. So this fits in, but it is comfortable. It is not comfortable because we spend this number of registers only for the generation of these positions, but there are obviously other processing after its generation. And also for larger grids, like for 64 by 64, it doesn't work at all, because the number of registers exceeds the limit of CUDA. So this cannot be scaled up very much. Slightly bit we can increase the size, but not much. So question, right? Is there a way to reduce this problem? And I followed with this question the practice of lawyers. Never ask a question for which you don't know the answer. We use another method to solve this problem. This is what I call the warp-wise implementation. The difference is that the threads in a warp work on the same problem. That is, one board position is generated in the threads of the warp at the same time. Different rows of the grids are stored in different threads. Essentially, what happens is that the while loop, which is here a temporal loop, which is executed a number of times, is executed here spatially in one step. As a bonus, we got rid of the divergence problem. Why? Because there is no loop. The loop is implicit in the special arrangement. And in the if condition, still there, will be still there, but the difference is that as all the warps are working on the same problem, and the decision if which way exclude or include the selected elements depends on a decision, but the decision is based on the whole warp, so all threads do the same decision. So either they all exclude or they all include, but there is no divergence. The threads continue to execute in lockstep. In the thread-wise implementation, there is efficiency, that is divergence, but apart from efficiency loss it poses, this divergence doesn't cause synchronization problem because divergence can cause synchronization problems. But in the thread-wise method, the threads do not interrupt each other, so there is no problem with this. And here is the code of the warp-wise implementation. Suppose there is a function called warp sum defined earlier. We'll discuss it later. And this is the code. We see that the 4 loops disappeared, and the only real change, only real interesting change, this one, this line. Here is the total number of selected elements in the whole warp, what is counted. The question arises how to count it, how to count different numbers in different threads, how to add them. This is called the add reduction program, and it is much discussed in CUDA literature. And it is solved, of course, but usually in shared or using shared or global memory. But since Kepler and later with a modified version of in Volta, warp shufflers exist, and they help us solve this. Especially this function is very good for us. The shuffle with XOR addressing and synchronized. The synchronization doesn't interest much us, but the XOR addressing is important because it means that we can achieve that all the threads get the same result from the addition. So that is all the elements of the warp of a given variable, all copies of a given variable in the warp are added, although in different order, but they are all ordered and delivered to the thread in very efficient method. As we do only integer, as we do this for integer problems, integer variables, there is no problem that the summation order is different. In floating point, it could be a problem because there is rounding, but in integer there is no such problem. So this is now I see this is the warp summation function. The critical instruction is this. This does the this does the real heavy lifting of the summation, but it's still a 5 size loop. But with unroll and inline, directives, we can achieve very efficient code. The 5 calls plus one addition is used only in each execution of this loop, and the loop is unrolled, so there is not real loop. One thing is interesting, that this word size function, CUDA function, is not good here because it is not available at compile time, and the loop will not be unrolled. Sorry. And here is the test. Again, we tested on the same card, and we had 650 million gates per second with this warp problem. So it is somewhat slower than the thread-wise implementation, but has the big advantage that it uses only one element in each thread, so that we have plenty of registers remaining. So we can with thread-wise we couldn't do 64 by 64 grid, but with warp-wise we easily do even larger than 64 by 64 solution with sufficient with suitable folding of the rows. So that's it. So my conclusion: warp-wise implementation is a viable option to mitigate the register storage bottleneck without using memory. Thank you for your attention.
Thank you for the nice talk. Is there any question?
Thank you for your presentation, sir. I just have a question about the CUDA Shuffle. As far as I know, the CUDA Shuffle provides a value exchange mechanism for the threads in the same one, right? So you can perform some reduction in the same one, but have you ever considered the values, like let's say on the edge between for example, I want to sum up all the values which cross a lot of warp, because it's cross warp, so we cannot perform the CUDA Shuffle.
Yes.
Works.
Yes.
Thank you.
Yes. The answer is no. I never consider using it for large problems, because I don't know a real application which is large and requires a specific number of bits selected. It is mostly for such problems than the games which I showed. So this 32 by 32 is itself is almost enough, because I don't know larger amounts of games. Yeah.
We have time for a few more questions. I'd like to ask, what are the uses of this and in this kind of
Yes, okay. It's multiple simulation of games when there are lots of tree searching and machine learning of a large number of positions, and random positions. I found them very usable. One wouldn't think that a random position is worth anything, but it is. The programs can learn from them, and they produce good moves in real matches. So there's and I need lots of them. So as a billion random game in 1 second is a huge search space, and even if the positions are random, the back propagation gives a good move from them. Of course, there is after the generation there is scoring and analyze and the main thing. But the main thing is that I generate a whole game in one generation without one by one steps, one by one moves, and that's the speed is the real advantage.
Thank you very much. I think we are moving to our next presenter.
Put up a microphone.
Thank you.
No? Ah, interesting. All right.
So next speaker is Yuvan, then who will talk about parallel EEG processing on GPU lab.
Okay. Hello, everyone. My name is Zhe Wang from the University of Pannonia. Today, I would like to introduce our parallel EEG processing work on GPU Lab, which is a GPU-enabled container-based distributed system. This work is contributed by my lab mate, Eva Sedika, and my dear supervisor, Zoltan Juhas as well. So the content will be grouped into 4 parts. First, I will introduce some background related stuff about what is GPU Lab and what is some fundamental knowledge about the EEG processing and why we need to introduce high performance computing into the EEG processing. And the second part, I will talk about our experience about using the GPU Lab, this platform, including the hardware infrastructure and access mode and our routine workflow on GPU Lab. And we did some preliminary performance testing based on some multi-GPU access tests, and that will be regarded as a final part. So before we talk about GPU Lab, first we need to know something about SLICES. SLICES is a short of scientific large-scale infrastructure for computing or communication experimental studies. Such a long name. It's a European Union project, and now we are in the starting community phase. In this phase, a lot of universities and institutions contribute to this phase together. Like, so there is an institution in Belgium which is called IMEC or IMEC. What do you like? It's Inter-University Microelectronics Center. So in their lab, they have a lot of testing platform like this virtual world, which can perform the large network and the cloud experiments. Like the City Lab is a kind of IoT testing platform for smart city construction. And this kind of home lab is kind of realized environment testing platform for the home environments. But our choice is the GPU Lab in this IMEC institution. And GPU Lab is a kind of distributed system for running jobs in GPU-enabled Docker containers. So users can provide a job destination file to the GPU Lab controller, and this controller will arrange the task to different clusters. And different clusters, they have different features. I mean, the hardware level features, different type of GPUs, different type of CPUs, and different size of memories. But we, as a user here, our task is EEG processing. First of all, our human brain is the most complex system that we have ever known. And the EEG, the electroencephalogram signal, contains a very rich pathological and physiological information of our brain activities. So it's just like a very convenient window for us to observe our brain activities. So in order to extract the real useful information and the real useful features of the brain activity to understand how our brain works well, and even treat the patient, like some epilepsy or stroke patient. So we need to process or analyze the raw EEG data collected from the subject. Here I listed several widely used EEG processing method, like the time frequency analysis, the connectivity analysis, and the source localization, decomposition analysis, and from the experiment paradigm aspect, we have this kind of resting states or task-related analysis. But the prioritization of this kind of EEG processing method is not the topic today. In the last year GPU Day event, I talked about our GPU parallel implementation of the multivariate empirical mode decomposition. It's a kind of decomposition, signal decomposition analysis. So yeah, our task as a user is an EEG processing. But why we need to introduce a high performance computing into this task? Because the EEG processing, it has several workload factors. For example, it's one of the biggest advantages of EEG, this method. It has a very high temporal resolution. We usually record the EEG signal with like the sampling rate used to usually is 1K or 2K hertz. And in some experiment, we need, well, at least, not at least, but normally it should be 128 and 256 channels. And if we want to analyze some correlation between different parts of the EEG signal, we may need a quite a long time measurements. So these four factors can very easily produce gigabytes level EEG data. And definitely we have, if we want to make our result or our experiment more convincing, we need to collect more subjects. So this factor here will multiply the amount of the data we collected from the subject. And another important thing is for the EEG processing, the EEG community, most of the processing script is MATLAB based. So it's relatively low efficient, and also because of the complexity of the processing algorithms, like the ICA independent component analysis and the empirical mode decomposition. There are a lot of iteration operations in these algorithms, so it's also very time consuming. But currently, we have several compromise solutions corresponding to these workload factors. How to solve this kind of high temporal resolution, I mean, high sampling rate, downsampling rate, from 2K, 1K hertz to 225, 55 hertz or 128 hertz. But we definitely will lose some information. Maybe it's some important information which can dominate the results. And for the number of electrodes, maybe we can reduce it to 32 or even less, 16 channels. But in this way, the spatial resolution will be totally destroyed. And for the long measurement time, we can chop the EEG data into several epochs. And each epoch only contains 8 or 10 seconds measurement data. But in this way, we cannot analyze the correlation between different parts of the data. And yeah, we definitely can reduce the number of subjects less than 10, but the result will not that convincing. Maybe it's just an occasion. And for the MATLAB low execution efficiency, we can transfer it to the C-based processing program, and we can optimize the algorithm. Maybe the time of space complexity will be reduced a lot. And yeah, that is the reason why we need to introduce HPC into the EEG processing, because high performance computing, or if we can provide some parallel strategy that is uncompromised solution. So let's be back to the GPU lab. Well, in the coming part, I will talk about our experience about using the GPU lab. First is their hardware infrastructure. As I mentioned before, the GPU lab contains several clusters, and different clusters has different type of GPU cards.
and we take the cluster 6 as an example. Actually, I think recently, just last week, they have a new one, which equipped with NVIDIA 800 or 800 parts, which is very powerful. But the cluster 6 is basically a HGX2 system from NVIDIA, and it contains 16 Tesla V100 GPUs. And these 16 GPUs are connected with through the NVLink that enable the GPU to access the memory in another GPU memory with a very high speed. And also in this cluster, it includes 16 CPU cores and 1.5 terabytes memory. That means if you have some CPU side computation requirements, this cluster can perfectly meet that. As I mentioned before, the GPU lab is container-based. So everything runs in container, and they provide two modes to access to their hardware. One is the interactive mode, and we will talk about this command line interface fetch mode later. For this interactive mode, they provide several default container images file. Like, for example, I'm quite sure that some of you are quite good at TensorFlow that build some neural network to train some data set and predict something. Then you can launch this kind of container. All the environments is perfectly pre-configured. You only need to upload your training data, your source code, and use a commander to compile it and execute it. So they have a lot of default container images file for this interactive mode. And this is the interactive mode GUI based on the Jupyter Hub. So this part is a storage space. You can see the data or the source code you uploaded. And here is the interactive shell where you can check the information of the system, including the hardware, the operation system, the workload, the real-time workload, and compile everything here is kind of interactive, just like the MATLAB or Python shell. And another accept mode is the command line interface fetch mode. So this mode is a little bit more complex. In this mode, we need to define a job definition file, and we need to send this file to the GPU lab controller, and the controller will analyze the content of this job definition file and execute the actions that you arranged here. We can go through this job definition file quickly. So the first thing here, we need to specify the path of the container we want to launch or mount it to their hardware. Well, as I mentioned before, for the interactive mode, they provide several default containers, right? But here, if you configure the very special programming environment and you can pick it up and upload it to the Docker Hub, then you can fetch it from here. Just specify the path of your customized container. And then we need to specify the bash script. So basically, this script will be executed immediately after the launch, after the container is launched. Then is a storage path specification, and here is the most important part, the hardware resource we want to allocate. In here, we can specify how many GPUs, CPUs, and CPU memories we want to allocate, and which cluster we want to use. And even they provide a minimum CUDA version here. And then is a schedule information, how long you approximately will use the hardware. But if you want to use it for days, you need to email the administrator of this system. They will allocate some special time for you. This full hardware or this several clusters will be your server only. And then it's a notification configuration. They will send you an email when your job is launched, it's running, or even when it is finished. After we finish this job definition file, we need to use this the command they provide to submit it to the GPU lab controller. Then everything is okay. Next, I will introduce our workflow with the GPU lab. So this part is our local development environment. Basically, it's our workstation in our lab or our laptop. And this part is a GPU lab clusters. So we designed the program definitely locally in our local development environment and debug, comparison, maybe some preliminary performance testing, just make sure the code is okay. And then we will upload the source code and the EEG data through the interactive mode to the GPU lab cluster. And in this interactive mode, we will edit this batch script that usually it contains the comparison step and execution step. If you want to measure the performance, probably the profiling step should be included into this batch script as well. And then we switch back to our local environment. When we finish the job definition, send it through the CLI mode. So all this performance testing, comparison, execution you define here will be executed in the CLI mode. After everything is done, the profiling result or the processed data is stored in the GPU lab cluster. So we switch back to the interactive mode and fetch back all the data, so result we want. So the next part, we did some preliminary performance test on this GPU lab platform. Is about the multi-GPU access. So we have 4 cases. The first one is the most naive one. We have a specified length of signal, and this signal will be handled or processed by 2 GPUs. So the signals, the input signals is divided into 2 parts, and GPU 1 will fetch the first half of the signal, process, store back. Another GPU will fetch the second half of the input signal after finished, store back. And the case 2 and case 3, we use a unified memory and a unified virtual address. So we basically allocate a memory which is available for CPU and GPU both. So in this case, we just allocate the inputs. We just allocate the memory for the input signal, and different GPU access their corresponding part after processing, store back to the managed or pinned memory. And the 4th case is about the peer-to-peer access pattern. It looks very similar to the naive one, but the difference is GPU 1 will the difference is, GPU 1 will access the memory in GPU 0. After processing, it will be stored back to GPU 0 as well. So the second half of the input signal will be executed in the same way. So it is GPU 0 will access the memory in GPU 1. After processing, it will be stored back to GPU 1 as well. And the input signal is processed by 2 GPUs, and we tested two different signal lengths, but with the same sampling rate, the 2 kHz. And the execution kernel is basically just multiplication and addition. It doesn't have any meaning, but we just want to test the performance. And testing hardware is AGX2 platform, and we repeat the kernel execution 50 times. So as we can see that the case 4 has the best performance, which we are quite surprised about this result, because I suppose this kind of unified memory or unified virtual address should win this game, because these memories we allocated, which is available for CPU and GPU both, they should be cached in advance. So probably I suppose their access speed should be higher, but the result shows, case 4 win the game. And no matter what kind of signal length it is, in 512 seconds or in 1K seconds. So several single GPU, single GPU based parallel implementation of the EEG processing algorithm have been developed, like the EMB related stuff I introduced last year, and also the independent component analysis and source localization. We achieved a very satisfied speed up, but it's still not enough. We need to continue to optimize them. And the most important point is the multi-GPU based EEG processing algorithm development. We have several strategies here. The most naive one is arrange one GPU for one subject, but different subjects has different signal lengths, different amount of data. That is just too naive, may not produce a satisfied speed up. So another strategy is arrange different EEG channels to different GPUs, or we can arrange different segments of the signal to different GPUs. So we will try to develop a most efficient way, for this kind of multi-GPU based algorithm. And then we are expecting to extend the EEG pre-processing pipeline to multi-GPU system, because in the EEG processing community, this kind of pre-processing is a very, very common used processing pipeline, because the raw EEG data is quite noisy. They need to remove the artifacts like the filter, mean removal, averaging, artifacts removal, and some statistical analysis. Everyone needs to repeat it many, many times. So this pipeline deserves to be transferred, to be implemented in a high efficient way. So we want to extend the pre-processing pipeline to the multi-GPU system. And definitely the research on the scalability of multi-GPU signal processing algorithm, just like what I mentioned, arrange different subjects or arrange different channels or arrange different segments in the signals to different GPUs. That is our future works. Thank you so much.
Thank you for the talk and advertisement for the laboratory. So we have time for questions.
Thank you for the excellent talk. I'm curious whether you also process sleep EEG, because you told that we need for half an hour long data, but the sleep EEG is more like 8 to 9 hours. It's similar.
Yeah, well, for the sleep EEG, that's a quite hot topic actually, because most of our lives spent in sleeping, right? So for the sleeping EEG, it requires hours measurement, right? So that's deserve this kind of multi-GPU system even more. But not only the sleeping EEG, and in some like stroke, because for the stroke patient, they need to monitor their EEG signal for a long time. They have some they have different seizures, but the data between different seizures also has some pre-alert meaning. So they also has a very, very, very long measurement. Yeah, this kind of long-term EEG measurement definitely deserve this kind of multi-GPU system. Yeah.
Hi, first of all, a nice presentation and nice project. So you mentioned that you are thinking to send different signals to different GPUs.
Yeah.
And I was wondering, based on what are the data that you use in order to separate each kind of signals? Because it is something common, or if they are very complex, or?
Yeah, it's a good question. The depends on the topic we want to focus. For example, if we want to compute the connectivity between different electrodes, like the electrodes we measured from the occipital and the electrodes we measured from the frontal, whether they have any information flow from this electrodes to another one. In this case, separate channels into different GPU is not our choice because they are totally isolated, so we cannot see the correlation. And in another case, like we want to, there is an interesting experiment which is called hyper EEG, measure two subjects electroencephalogram at the same time and to see whether they have any correlation together. So in this kind of experiment, separate different subjects to different GPU is not our choice. And basically that is a strategy. And for different parts of the signal, probably, I think if we have a very, very long measurement and we want to compute the continuous correlation in different segments of the EEG signal we measured in a very long-term measurement. Well, in this case, I suppose divide the signals into, in the time domain, chop the signals into different GPUs is not a smart choice. So basically, it depends on the topic we want to focus. Yeah.
Yeah, that's good. So just another one, was very short. I was wondering which kind of tasks do you the subjects do while you.
Okay, well, we have a lot of experiment actually, but currently we are doing some neuroaesthetic, some cognitive related experiment. We show several pictures, painting, some of them are abstract paintings and some of them like created by Picasso, that kind of corner, rectangle, triangle stuff, very, very abstract. You know nothing about it, at least for me, because I'm not an artist. And another data set, let's say, is figurative pictures, like it's just sceneries or anything that you can realize, you can recognize. And we want to say when people appreciate these two kinds of paintings, what really happened in their brain, or how the brain will respond to different art style. That is our current project, but we have some other project like the finger type, because we even cannot figure out how our brain processes this very simple action. So what really happened when we tap our finger? Like we use mouse every day, we tap it, so we need to make a decision, and decision making is another great topic. So we need to make the decision, and the motor area will be stimulated and perform the action. How the information will flow from different regions in our brain is a very complex system. As I said, the brain is the most complex system we have ever known. Yeah, that is an experiment we did before. Yeah, thanks.
So, is there any more questions? Then let's move on to our next speaker.
Please answer. Go ahead.
Yes. Better.
Ez a tovább? Igen.
Ugyanígy ezen is tudod.
Jó, engedj.
Csak hogyha a laptopot akarod, akkor ez is megszívül.
So next speaker is Könyves. He will talk about sector results of ILAP. So I give you the word.
Thank you. That's right. Thank you very much. I'm Vera Könyves, and
I'm an astronomer turned data scientist, and until last year I was working abroad, after which I joined the informatics laboratory of the Institute for Computer Science and Control. And I'm going to present to you a couple of results of MILAB, which is the Artificial Intelligence National Laboratory in Hungary, because basically, well, this is a hub of experts and institutes on AI, and that is absolutely relevant at the GPU Day. So the head of MILAB, that's András Bencúr at Stucky, who is holding together 11 institutes in the consortium, including a couple of universities, research institutes, and even a law enforcement organization. And we're also collaborating with external industrial partners who are present in Hungary, such as, well, up there you can see Audi, Bosch, or Ericsson, or Nokia, etc. Well, more interesting things. In MILAB, the research is organized in 6 work packages, starting from fundamental mathematical research to machine perception, which is István Csabai's, well, one of István Csabai's expertise, then NLP, medical, health, and biological research, a more industrial one, sensors, IoT, telecommunications, and we are covering security and privacy as well to ensure that there is not going to be failure in the AI systems, basically. And as we are there at GPU Day, I'm showing to you in red the computing facilities that our colleagues are using in the different work packages. For example, the Wegener Scientific Computational Laboratories resources, the academic cloud, and at the institutes here and there, for example, at Stucky or at Rainy, their own 800 GPUs. Oh, a couple of more words about the relations among research development and industry, because this is interesting how this is organized in MILAB. So the dark blue box, that is the AI laboratory. In data and solutions, they can come from outside of the lab by collaborating with from collaborations with the Digital Heritage National Laboratory, where there is corpus development or large language model teaching is going on, for example, in the case of language applications. And in other fields, we are also collaborating with other national laboratories like health-related national labs or the Autonomous Systems National Laboratory. We are developing at MILAB language technology, for example, then machine perception technology. And for example, the theory in work package 1 could tell and figure out how and why these large models, large language models are working. In the security work package down in here, that is giving us then supervision and operational guarantees. In terms of applications, then we might stay in-house or collaborate again with other national laboratories, as well as with domestic industry. And now we'll go to into a little bit of science, natural language processing researches in NLP, and we will stick to that for some time because of this hype, this very recent hype and very real hype around large language models and ChatGPT that someone already asked whether everybody already used that, because obviously that is the case. I already used that for generating the abstract for GPU Day. But that has been reworked, obviously. So this is Hugh Spacey, highly GPU-related, GPU-demanding task. Our colleagues at the Szeged University, they are teaching 4 different models of different sizes for Hungarian language preprocessing tasks, such as tokenization, sentence splitting, part of speech tagging, for example. And these publicly available models, they are all large language model based on, for example, the Hungarian BERT and or the multilingual Axel and Roberta transformer models. This is another research, NLP research from Szeged. Our colleagues, they are using the Hungarian question answering database called Milka, from which they are teaching extractive and abstractive question answering systems in Hungarian. In this mecha corpus, they have drawn about 10,000 question answer pairs of different types, such as yes and no questions, or arithmetical questions, or questions that cannot be answered from the text. And what is also an important thing to mention is that they were using, based on the metrics, they were using only good quality Wikipedia articles as context for the questions. But then like this, therefore, if you would build such a method in a chatbot, that would always be factual, as much factual as the Wikipedia articles, without any hallucinations, and the underlying knowledge is also quickly updatable. You do not need to retrain your model. This is now a little bit of fun time. This is an example of a factual error. In the original input article, this is about an abused man, while in the summarization, the model really felt necessary that it's rather the opposite what was happening. So he beat his girlfriend, which is not really funny. But then this next example on hallucination is absolutely an adorable solution. The model here says that Jensen Button is the Secretary General of NATO, while there was nothing any close in the original article. So this is,
Maybe the next.
this one is really cute. Yeah, what else? Okay. Another NLP project, again from Szeged, now by Gábor Berend. So they are pre-training models in different languages so that they could become compatible with each other. Let's say you want to process your Hungarian text with a model which has been pre-trained, pre-processed, pre-trained in Hungarian, and then at some point you want to change to another model which was pre-trained with another language. So down in there, that's a Hungarian Shepherd, and up there, that is English Bird, and in between, you need to then use a kind of linkage or mapping to then link these two parts of the different languages. And what made this project GPU intensive is that they tested 16 languages. They were using different layers where to cut basically the two half languages, and they were also using different learning strategies for the mapping to figure out what this mapping will be. Again, another project from Gábor Berend. Imagine that you want to train your favorite language model with such a sentence: Alice is eating a cake. That's absolutely relevant in here, right? Alice. And then randomly you pick a word, for example, cake, and you put a mask over it, and then you want to recover this mask during the pre-training. And what our colleagues, what they want as a preferred output is actually that they get a probability distribution over the vocabulary, not only that original and only word cake. And why? Because they are saying that basically because from the human cognitive point of view, these other words as well, which are marked in red, brownie or spaghetti or a cake as well, they could have eaten. So they like probability. And now let's stick with NLP, but we will we'll just put a little bit of, evoke a little bit of theory and applications as well. But in fundamental research, which is not really NLP related, we all want a good cost accuracy trade-off. That is that for a given problem, you do not necessarily need to train your biggest model when a smaller one would give already good enough results. And also there are ways to optimally use your available data and thus alleviate data hunger. For example, we are also using environmental information, and we want to build in knowledge graphs in our models to ensure factuality over and above the language models. This is a nice paper by a colleague of mine and et al. So Béres et al. And nice results. They were investigating vaccination views from tweets from 2021. And pro-vaxxer and vax skeptic contents were also analyzed after they have been labeled. And in this table, you can see that based on a certain metrics area under the ROC curve, the best performance was given to a model which was trained on COVID-19 related tweets. Then the small BERT model, this is also featuring high up there very well, while the large BERT model down in here, that is not featuring very well. But this is not necessarily the case that a larger model is featuring worse. It is just that here, that's what happened. All right, within the same Béres et al. Paper, the goal was that they wanted to demonstrate the importance of network effects. And they deployed several node embedding models. They also used vector-based node embedding by Vokelets. And this gave back very well the hierarchy of the topics. For example, in this colorful image, you can see anti-vaxxer topics, and in the center, whether you can read it or not, but there are anti-vaxxer topics related to child death. Those are the violet ones, and below topics related to fear from mRNA techniques or technology, and some other ones are related to politics, less offensive topics, or related to what I'm reading, the legend, medical arguments. And yeah, these are nice topics, whether vaccine skeptic or pro-vaccine, they both had in their papers. But if you want to know more about graphs or vector embeddings, please consult these references and papers. Some theory now in the time of large language models, because if you have a large language model, for example, a large model, you might want to know why and how they are working. Because recently, deep networks, they are actually showing something interesting, which is called a double descent. This phenomenon, which is shown by the blue curve in the test train error versus model size diagram. And from the classical statistical learning theory, we know that the bias variance trade-off is an important concept that you will know. When your model's complexity would pass certain threshold, then your model will overfit, the performance will go down, and then the test errors will go up. And that's it, up to the red line in there, the dashed red line. But with increasing the model size, deep neural networks, they are showing the blue curve down to the end. So there's going to be a second descent of test errors as well. And our colleagues, the theoretician colleagues, they also want to understand better this phenomenon. And knowing also that the classical and the modern regimes are also referred to as the under-parameterized and over-parameterized regime. Let's now change to the next slide. I think I know what is coming in here. And yeah, so basically, the left-hand side panels, there are visual illustrations of double descent and their connection to smoothness, where the upper left panel, that would be considered a good fit in case of a few parameters, while the panel next to it, that would be a good textbook example of overfitting. And down here, if you're increasing the number of parameters even more, then it will result in a much more reasonable and much more smoother curve. And with all these, I just wanted to say that you might track and trace and analyze your double descent in the function of what I showed you before, the model size or the number of parameters, or in some papers, even in the function of the number of training epochs. So there's still to discover in this double descent issue. And now we know how and why our models are working. We also, it's also wise to ask so what the limitations are. About that a little bit. This is still NLP and or not a little bit of theory, but just to get to know better the limitations of neural network generalization and reasoning. Actually, these gentlemen down in here, they introduced a benchmark, which is called PVR, pointer value retrieval, which is based on human-like reasoning. The fact that humans are able to process indirection, and indirection is a multi-stage reasoning process in which the first stage would provide information on subsequent tasks. And in the case of the PVR, how it looks like is that there's a pointer. That's the first task, which is the top left image in these example images with the numbers and in the MNIST and CIFAR database elements. So the pointer is the top left image, which would give indication for the next image to be examined, which would be the second task. In other words, if the digit in the top left image is 0 to 3, for example, that would indicate for the second task the image to be analyzed in the upper right corner. And so on and so forth. These authors, they were analyzing, they were testing in this benchmark various neural network architectures, several data set sizes, and also different complexity of tasks. And they found that in a couple of cases, the neural networks, they fail, and in some other cases, the neural networks succeeded. So obviously, we can make the neural networks fail. There are some tasks that they are not able to process, but this we already heard in previous talks as well, that can happen. Well, neural networks, they don't only have limitations, but they might have security issues as well. And colleagues from Szeged, they showed that numerical rounding and floating point errors, so they can be exploited to craft adversarial networks, which can then be used to insert backdoors in your network that the verifier wouldn't even find. So they would just miss these backdoors. And in this paper, they gave defense against this problem. But for more details, please go and see this paper. And yeah, now that was all of NLP or not, we will see. But now let's switch to some machine perception, medical health and biology projects, a couple of examples. But here as well, a funny thing that here as well, we might discuss a little bit the promise and perils of large language models. Because in, what happened? Yeah. Because in some medical tasks, it has been already shown, for example, by colleagues in Szeged as well, that large language models and NLP can be built in, but these are not always very applicable, depending on the very medical case. In some medical image analysis problems, for example, large language models cannot be used because each and every problem might be different. And I think two medical projects I will mention in here. Both are currently running on GPU Lab. Is that the same GPU Lab that you presented us?
In the Belgium, I'm in the university, microelectronics. If so, that is the same one.
Okay, so I'm not sure whether it's the same GPU lab in here or not, but anyway, these are currently running, and these are both the work of István Csabai and group. So in order to understand the evolution and within MILAB, that's why I'm talking about this. So in order to understand the evolution and functional properties of influenza virus, they were looking at how to predict the phenotypic properties of the flu virus, considering only mutations in the genetic sequence alone. And the machine learning that they were using in this project, that was the prediction of 3D protein structures about which, done by AlphaFold or with AlphaFold, for example, about which we heard a very nice presentation yesterday. I remember that. That was really a nice presentation. And they were also predicting the phenotypes. And as this is currently running, this is an ongoing project, but it can be considered as the continuation of their last year's project on SARS-CoV. That was very timely at that time. And it ended up in a very nice paper, in a very prestigious journal, actually, Nature Scientific Data. So congratulations. And another project of István Csabai's group, I think there's going to be a talk about this after today's, these guys are nodding in there. So I'm just flashing it up. I'm not going to talk about, I cannot even about more details. I'm just telling to you that this is a medical image analysis project for a machine learning competition to predict stages of breast cancer, and only handling the data was a challenge, I know, from Pista. And the techniques and the smart techniques of these guys, they won for them the first place of the first and the second round of this project. You can see the leaderboard here at the Nightingale contest page. And basically, then that's it. More will come from them. And I might have used up my time. Yeah, I don't know, but maybe I will just hang up in here. And many thanks for your attention. Thank you.
So thank you for the presentation. Is there a question?
So you have mentioned some large language model projects here, and and of course there's ChatGPT. And is there a possibility to cooperate between these models? So you define the strengths of the different models.
Well, don't ask me very specific questions, because then I will point to you the right person within the consortium. But what do you mean by combine? So what I know is that within their projects, our colleagues, mostly from Szeged, that's the center of the NLP studies there within the MILAB, they are testing actually several models. The similar tasks, what they have in mind, so they are testing on similar models. And one which I mentioned by Gábor Beren collaborators, and whom want to combine them, actually, even they want to combine the way that they cut half of this and then put the other half next to it. So I do not know actually what exactly means to combine even. I'm sorry for that.
All right, anyone else?
For the presentation, I have two minor questions.
Could you please shout a little bit? Even in the mic. That's all right, but just a little bit louder.
Okay. I think this is the first ever presentation, which I did the last 2 days, that both covers somehow both complexity theory in the slide 20 and both somehow touch the hearing completeness. That's the unnecessary problems. And I just want to make a remark that even occurred some areas non-convex with optimization problems, but nobody is realizing there are in operational research that generalize somehow the semi-definite programming, and they introduced another classes of matrices with the so-called sufficient ones, which can all which can provide their solutions in a polynomial time. And some classes of machinery and programs can be formulated in a way server based to obtain such models that can be solved efficiently. And I see several paths in the future that you can other technologies can get for this area as well. And the other one is that is so obvious that anything that is Turing complete or Turing equivalent can be difficult. It is this area and slide 24 and 25. For example, there is a existing construction that renders fully inverse atomic machine that was the claim of life, which imitates this biological model. And imagine that if there is a doctor which inspects the sample from tumor cells, and from the sample in the pattern, the two-dimensional pattern, one must decide the doctor whether it needs curing or not, because we cannot even say in general case there's an condition that it will sink or it grows intensely infinity the population of the sample. And these are just my remarks.
Okay, thank you very much. I mean, absolutely taken.
Is there any other question?
Thank you. You mentioned that different national laboratories can collaborate. So how does that happen?
Well, this is a 5-year project, a national laboratory, and I wasn't there when it was created. What do you mean by how does it happen? So we have actually, obviously, there are some other steering organizations even above the national laboratories within Hungary, because there are more. But within this one, I mean, there is a head, and there are some other the leader of the leaders and organizers of, well, the scientific packages were discussing when and what I don't know, meetings or brainstorming or events to create or hold. Or within, well, there are also mailing lists where the researchers of MILAB are actually all together in, so we can also spread some information among us, and we find each other within this network, within this national laboratory, easier than someone who is not within this laboratory. What do you mean by something like this in practice?
Personally, I'm very interested in real problems and project for it. And that's what I wasn't here yesterday, but because I'm following the talk is I will watch the video. And how can I, for example, reach out to someone who is working on that? Does that happen often? Can we?
Oh yeah, then I can tell you, because I also mentioned that then it won't be me, but I can maybe point you to the right person. And after the coffee break, guys they are within the same group of István Csabai, and please go and talk to them if you are interested in the AlphaFold, for example. Yeah.
Just a very question. So how do you measure the social impact of the MILAB? So when something is, I mean, because what you presented, it was mostly science. So, but what is the benefit for the society of this, and how can you measure this?
Well, telling the truth, I have no idea. Ask András. That's good. No, well, what I also know is that well, there are some other helpers, not only the head of MILAB and the researchers, but there are some other people who are responsible for either international relations or industrial relations. So you are reaching here and there as well in industry and internationally as well. But I do not know whether and they also have to return, I think, per half a year or per year, some documents that I have no knowledge about what's inside and what the metrics are, for example, whether this is a successful project or national laboratory or not. So I have no idea.
So, thank you.
Thank you.
We should move on our next speaker, which is Ákos Sudár.
Van változás. Feltöltötted a honlapra. Jó. Megnyitjuk. Dolgozd magad. Okay, could you hear me?
Nice and clear. So let's begin.
Okay, welcome everyone. I'm Ákos Sudár and I will talk about the Richardson-Lucy-based image reconstruction algorithm for proton-computed tomography. But how to say, most likely most of you don't know much about proton therapy or proton imaging. So I will start with our motivation and background. So first of all, how to imagine CT. So what to know about a CT imaging? That it's something like we use some type of particles to get to reach information about the patient. So it's a bit like here in case of proton-computed tomography, we have protons and we have high energetic protons which go through the patient and lose energy on the patient and stops after the patient in a detector. And so we can collect some information about the patient, about some type of density of the patient through the proton line, but this information is kind of integrated through the lines, and we would like to know the spatial distribution of this some type of density. I will go back, that is this density, it's not as clear. And we would like to store this information in a kind of 3D array, so practically a 3-dimensional image. A pixel of this image, a volumetric pixel of this image is called voxel. And okay. Most meglépni nem tudok éppen. Okay, now it works, thank you. So what we can do that here you see a section of the patient. So for example,
session like this, and sorry, slice of the patient. And what we can do that we use several protons to imaging. We collect integrated line integrated information about this density in several positions from several directions, which can describe like matrix multiplication. And our task is to reconstruct the original distribution from these line integrals. And sometimes it's practically the inverse problem of the matrix multiplication here. Sometimes this inverse problem can theoretically derive. It's like the filtered back projection in case of any X-ray CT, but it's not so straightforward in case of proton computed tomography, as the paths of the protons are curved. But still, we have some chance to do it, and we use iterative image reconstruction techniques to reconstruct this density. And what is this density? It differs from modality to modality, and that's what makes the difference between CTs. And for example, in case of traditional X-ray CT, it's the linear stopping power, linear attenuation coefficient of the X-ray photons, and with these photons we can reach anatomical information of the patient. But CT is also used for functional imaging like MRI or SPECT, when we collect information about a pharmacon distribution in the patient, which is related to some biological processes. But in case of proton CT, we do neither this nor that. Okay, finally we collect some type of anatomical information, but we need a special type of anatomical information. And why do we need this? Because we want to calculate the stopping position of the proton beam in case of a proton therapy. So our ultimate goal is to support proton therapy image. So proton therapy treatment planning. And in case of proton therapy treatment planning, they use proton beams from different directions. And here we have a volume which is a tumor, and our goal is to focus the direct peak of the protons into this tumor. And to do this, we need to know the energy loss of the protons in this path. So practically, we need to know the range of the protons, but we cannot directly measure them. We measure this range because the proton stops in the patient. But we know that the range of the protons is characterized by the stopping power of the materials. But the problem is that the stopping power both depends on the material and both depends on the energy of the protons. So on its own, it's not so practical to not a practical unity, so not a practical constant, so not a practical, not really material property, not a practical property to characterize this range, because if we know the stopping power for certain, so we would need to know the stopping power of the material, of each material type in the human body for each energy, and that's what we don't really do. But because we have a fortune that okay, if we normalize the stopping power of human tissue with the stopping power of water, then we got a more or less constant. So we got a more or less energy independent value, and this is can be used both for imaging and for proton therapy treatment planning. So what I'm talking about, that okay, the stopping power in the imaging range is okay. First, it's changing. Second, it's it's half of the stopping power, for example, power than in a treatment energy range, and in the treatment, in the range of treatment energies under 100 MeV, the stopping power itself is changing a lot. But if I calculate the relative stopping power from it, then it's much more constant, as the kind of maximum deviation between above 50 MeV is less than 3%, and the deviation of the relative stopping power. So how to say, the energy dependence of the relative stopping power under 50 MeV can be much larger than 3%, but it doesn't really matter because the range of the of 50 MeV protons is very small, so it's not really not really contributes the range here. So it's just some small error here. So all in one, our goal is to create an accurate map of the relative stopping power of the patient, and we want to use this for more accurate treatment planning than the treatment planning of these days. These days, they calculate the relative stopping power from the Hansfield unit taken by traditional X-ray CTs, but this conversion is not direct, so not trivial which Hansfield unit connects to which relative stopping power. It's upon the material, so this conversion increase the error of the relative stopping power, and this error what we wanna avoid with directly measuring with the proton beam. Another advantage of the measuring with the proton beam is that we can use the same. So how to say? Yes, we can use the same, really the same device for imaging and treatment as well. So maybe some small uncalibration error is a calibration error. Maybe doesn't really matter because it's both included in the imaging and the treatment planning and in the treatment itself. And the Bergen PCT collaboration was established to design a proton computed tomograph detector, which is visible here. And the main concept is to use silicon pixel detectors both for measuring the outgoing direction of the protons and the remaining energy of the protons. The remaining energy of the protons is measured by a sandwich structure detector, which is built of alternating absorber and silicon pixel detector layers. And this detector system is designed to measure 1 million protons in each second within a quite small area, is around 1 square centimeter. And okay, so let's go back to the image reconstruction, which was my task. And what I wanted to, so I needed to reach the relative stopping power of the voxels from the measured information of the line integrals and the approximated interaction coefficient between the proton passes and the voxels. This interaction coefficient, so I imagined this interaction coefficient like the expected pass length of the proton in a certain voxel. Traditionally, they say that okay, the proton went through the most likely pass of the proton, and then they calculate with the pass length of this estimated proton pass in a voxel, and I try to how to say, step forward and say that okay, but let's include the uncertainty of the information about this proton pass because it's just an approximation, but it can be a bit left and a bit right as well. So the proton can go through a bit left and a bit right to the most likely pass. So its pass is not really a line, but it's a probability density distribution, and I consider this probability density distribution during the image reconstruction. I use the Richardson-Lucy algorithm for the iteration cycle itself, and the Richardson-Lucy algorithm, which is visible here, describes how to. So first of all, we have to take. So we have to make an approximation for the image, and which can be a unity array. And after we update all the voxels, and the Richardson-Lucy algorithm describes how to update these voxels. First of all, let's multiply the previous estimation for the voxel value, and after multiply it by a by a normalization coefficient, which kind of includes how many interactions happened with that voxel. After let's multiply it with this summation, and this summation is it's kind of a weighted sum, and the weights are the Hadamard. So no, the weights are the interaction coefficient between the different protons and the voxels, and it sums the Hadamard ratio of the voxel. The Hadamard ratio of a proton describes the ratio of the real of the measured energy loss and the calculated energy loss based on the previous iteration step. And yes, as it's a very computationally, so how to say, as this iteration cycle requires a lot of computation, I use a GPU parallelized code to calculate to run the cycle and calculate the relative stopping power distribution. And here I want to show some results. And first I tested the convergence of the algorithm. Then I used an imaging model without uncertainty and without measurement uncertainties. And like this, I can show that the algorithm itself converges very well. But it's notable that as the probability density distribution becomes wider and wider, the problem becomes less well conditioned, so requires much more iteration to converge. And after I turned on how to say measurement errors, practically I used the Monte Carlo simulation. And the main point here that we had a real proton path, but the most likely proton path diverged from it, and we can only say that okay, the probability of the real proton path is a Gaussian distribution around the most likely proton path, and I modeled this one, and it's a like that. Okay, so how to say the path of the proton, which was a line earlier, becomes probability density distribution, and here you can see the kind of model of passes of 5 protons. And with this, I have tested first the spatial resolution of the reconstructed image, and I reached 2.1 line per centimeter spatial resolution, which is worse than the 3.2 line per centimeter for proton CT, for the kind of the best proton CT setup of this kind. Okay, that there are better proton CT setups, but they has other disadvantage than our setup. And I have tested the RSP accuracy of the algorithm, and I have reached similar results than the literature, which is fairly enough for treatment planning. And as a summary, I applied the Richardson-Lucy algorithm for proton CT image reconstruction, and I reached reasonably good relative stopping power values, but my algorithm is lacking on spatial resolution. So the next step would be that let's revisit our approximations and simplifications, and yes, let's try to find which one of them caused the loss of the spatial resolution. And thank you for your attention.
Thank you for the talk. Is there a question?
Thanks, Ákos. Can you go back to this linear relation between the voxels? Right, this one. So here what I understand, Y is what you measure, this is energy loss at the end. More or less.
Yes.
X is what you want to know. This is somehow you want to characterize the material.
Yes.
And A is the interaction matrix from proton voxel, and only formally you assume that you know it, but you never showed us what it is.
Yes, formally I assume I know it, or at least I know it much more accurately than the energy measurement. And it's an unclear question if this is, how to say, assumption is good for proton computed tomography or not. In case of a traditional CT, where the, how to say, the beam which goes through the patient localized very well, expect the scattering, but otherwise it's, but if I can reduce the scattering, it's localized very well, but I have a high inaccuracy in the measurements through the line. It's not energy then, but okay. So how to say, yes, this formal assumes that the measurement of the energy loss is much more inaccurate than the measurement of matrix A. And the matrix A is calculated, yes, kind of based on this distribution. And this distribution is, so practically the most likely path of the protons are approximated with third-order splines. And after I calculate the distance between the center of a voxel and this line, and based on this distance, I assume, how to say, Gaussian probability density around how to say, around the most likely path of the proton, and I how to say, assign a coefficient for the voxel based on this Gaussian probability density and based on the distance between the spline and the voxel.
Does it mean that it's different from particle to particle?
The interaction matrix. But yes, each particle of the interaction matrix is one line or one row of the matrix A. And so it trivially differs from particle to particle. And yes, this is required to reconstruct the image.
All right. Is there any other question? So then let's move to our last presenter from this session.
Thank you.
So our last presenter is Bence Dudás, who will present his work on proton computed tomography.
Can you hear me? Okay, so my talk is pretty much related to Akushi's talk because we are kind of working in the same project, but in different part of this project. So what we do is data analysis with neural networks and for the proton computed tomography, but in different part of it. So later you will see. And I'm Bence Dudás. I'm a master student at Florence University. So just a quick reminder. What Akush already told. But anyways, so let's refresh our memory about this topic. So in cancer treatments in general, so when we want to treat cancer, there are some things that we need. So we need to locate the cancer cells, and then try to destroy those cancer cells in a manner that we want to minimize the harm in the other healthy cells. So in other words, we want to minimize the risk of the treatment. And for that, there are multiple approaches. For example, there is surgical approach where surgeon just operates on the tumor. There is the chemotherapy where some kind of toxic chemical used against those cells, and there are also radiation therapies where some particles are radiated into the body to destroy those cancerous cells or the tumor. And hadron therapy or proton therapy is a kind of this treatment. It's a radiational one, and it uses the Bragg peak of the protons to achieve this goal. And the reason it is an important one or a good approach to treat cancer is that unlike photons or electrons that are deposit their energy mostly when they go into the new material. So as you can see, protons are depositing it in a different manner. So as you can see, it can be calculated when the protons will deposit most of their energy, and by that destroying the cells. So in our case, the cancerous cells that we want to remove from the body. And by that manner, it's easier to, or by this approach, we can minimize the harm done in the healthy cells, and it can be used as an ambulant treatment, so it does not need many repetitions to do this one. But to be able to do this, there's a need to tomography, which is in respect for the protons, so what the protons will go through and how it will, so what kind of stopping power are applied on them. So for that, there is the proton computed tomography. And as Akush had already talked about it, in proton computed tomography, there are protons that high energy protons, so in that manner they will not do any harm in the patient. So they are beamed through an object called the phantom and scattered and captured by a detector system, which Akush already shown us how it looks like. And from that, this is where our books are divided, because Akush is working with the data that is extracted from the detector system. And what we are trying to do in our research is to trying to extract the data from the detector system to the image recognition, so the image creation, which Akush is used. So what we want to do in our research is trying to reconstruct the trajectories of these scattered proton beams. And we also, so we want to do that to be able to get the scattering angles, so in which angle they scattered through that object, and also we are trying to get the energy deposition which they did. And for that we use neural networks, and the data which we use is a simulated data to annotate these trajectories for the supervised learning purposes. And so our data consists of an unknown number of finite data points. They are so the number is unknown because we do not know exactly how many particles are going to leave or may leave the detector system, and there is always a possibility that some particles are created inside the detector system, and sometimes they can be mistaken for scattered particles. So we do not know at first which are the good ones and which are created or living. And also these data consists of 3 positional dimensions, the X, Y, and Z, where Z is just the identity of the detector layer which they hit, and we also get the energy deposition of them. And for a 2-dimensional purpose, I have shown you so in the left side panel, there is the detector hits on the first detector layer. As you can see, the number of these hits are seemingly much more than in the detector hits in the 21st detector layer. And also their energy deposition is shown by the size of these hits. So it's also can be seen that in the right side panel, the size of the hits is much greater, just because they are protons and they are trying to, they are starting to deposit more and more energy here. And to process these data, we choose a very promising deep learning architecture, transformer model, and later on I will try how did we use these models. But for those who are not familiar with deep learning or with transformers, these models are actually introduced to solve natural language processing problems. And they are very good for these purposes because they are strong in time series predictions. Because with the transformer models, they introduced a so-called attention part, which uses the information for previous predictions in the model, and that can be used for prediction, unlike this recurrent neural networks, where is always just the previous predictions are used. So for those who know some about transformers, what we did is we put the keys and the queries into the X, Y, and energy deposition values. So it's actually just an encoder. It does not have a decoder part, just because it's not a natural language processing problem. And for the targets, we give the free and theta scattering angles and also the kinetic energy of every trajectory. So how we try to approach this problem in the sense of machine learning, what we did is just iterated through every detector layer from the last one. The last one is necessary because there are the lowest number of proton hits. So, and yeah, I did not mention that we do not want to get as many trajectories as it is possible. What we want is that the trajectories which we predicted has the highest confidence as possible. So the ones we predict, we want them to be sure to truly that they are what they are. So this is why we started from the last detector layer and then iterated through every previous one of them. And so while we did that, we tried to connect the positions with respect of the previous ones, and then tried to predict these values, so the scattering angles and the kinetic energy of these protons. And also we give every time data, so after every iteration, a random permutation, because we do not want the model to memorize the values that they come after each other, but we want the model to be able to connect these values. So for simplicity, our data as something like this. So we have the X and Y position, and also the energy deposition of a specific layer, and also the XY and energy deposition of the previous layer, and the P theta and kinetic energy of the previous layer, which is would be nice that we could feed the model the predicted values. So far, we are using the target values to strengthen the prediction of the model. It is simplified because inside the model we included some embeddings and yeah, to show that it would be like a bit much more harder to look at. So the target values are just the phi, theta, and kinetic energy, which we want, corresponding to the layer where we want to get these values. And as I said, even though in this picture the particularities are the same, in the real world it's not, so it's always shuffled, and then the model tries to connect this. I just did this to visualize this data. And for the results, what we had, we started to go upwards in the sense of number of tracks. So in the beginning, we started with a lower number of tracks to train the model, because as I said, the more tracks there are, the more complex problem it's to be able to connect a certain data point with the one it's connecting to them. And as we go up with the tracks, the learning curves of this model were kind of promising. So as you can see, it has some noise in it, but in general, they are showing some kind of learning during these sessions. But when we started to analyze the results, which we had as in the theta scattering angles, or predictions was like, so as you can see, they are not that good. Even though in the phi scattering angles, the predictions which we had were at least in the same scale as like the target, and also the kinetic energy. So, but here you can see there was a mismatch, because this value does not belong to this one, but for the one next to it. So, yeah, our model can mismatch values, and for that we need to do some fine tuning and trying to fix these problems. But at least it's finding the scales, and it can learn and getting better and better results every day. And this was my talk. Thank you for your attention. And I also would like to thank for the support my supervisors, Dr. Gabor Pap and my mentor here at the Wigner, Dr. Gabor Biro. I also would like to thank for the Artificial Intelligence National Laboratory for the support, and also the Wigner VSC Lab for the support of my project. Thank you very much.
So thank you for the talk. Is there any question?
First of all, it's very useful. I have two questions. The first one is if you know about other research in this area and like how far it is at the moment, what stage, and then if this would in the end be evolved into something that is very well tuned, that would be better in the other one to get down. Yes.
In general, with hadron therapy, I guess is the question. Actually, my participation in these researches, it's not that's highly connected to it. So I'm not from the medical side of this research. As far as I know, it's an active kind of treatment. So there are places where you can get, so anyone can get hadron therapy as a cancer treatment. But as Ákos mentioned, for the tomography part, they have different approaches. And this is, so for that one, we want something that is more accurate for in the respect of the proton. So it's like, when you do any kind of tomography, so MRI and CT, etc., they are very precise in their way, but not with the respect for protons. And this is why we do this, because we want tomography which is especially good for protons.
Illustrate the ranges here that the proton deposits 90% of its energy within 1 millimeter. It's very effective. But since we cannot really use directly the CT information, but it's a real therapy, they add 1 centimeter additionally to be safe. And that can be improved.
Is there one question? Yes.
So, can you hear me?
Yes, I can.
So, you talked about input data. Okay.
Yes.
So, is it a simulation data? And how large is it? So, you mentioned you train transformer layers and copper layers. So, it's quite relevant how you get your data sets.
Yeah, so it really depends on how much data which we put into the system, because so far we are peddling those. The number of tracks can go really high, like in the, so here, and you can see like thousands of hits can happen in a detector layer. And yeah, so what we give into the network itself as these currently not that many, but the goal is to give the layer these hundreds of hits on every detector layer, padded into maximum amount, and
did you consider? Okay, so question. Do you train from scratch, or you use any pre-trained weights, architecture, or anything?
Yeah, so so far we are training from scratch, so not using any kind of transfer learning.
Okay, so because I will mention you that you may download some pre-trained transformer layers and encoder parts on your so you can do it whatever. And because you have very little samples. And from my practice, so what I see, it's really hard to train those networks from scratch. So I decided to do that. It will be an experiment, so you will see. Yeah.
Really deep setup.
Okay.
So where is it now around 1 million?
Yeah, so going up to million scale is a very cool. I think. So yeah.
All right, and I think we should hold a short happy break. After that, continue with our last session for today.
Kikapcsoltam a nezörögöket.
Igen, jó, akkor nem tudom, hogy
Well, idiot check, can you hear me? Okay. Maybe F5 will start the presentation mode. Okay. Wow. Okay, maybe try with this button here. And oh. Okay. So thank you. Good afternoon, welcome everybody. My name is Tomáš Saba from Budapest University of Technology and Electronics, and my talk is titled GPU Accelerated Parallel Computing of Iterative Function Systems in Mechatronic Applications. So main topics will be position control tasks in mechatronics, and a very unusual approach to examine this problem with iterative function systems, which is a fractal theory approach, and an efficient implementation of iterative function system evaluation on GPU, and we will see some simulation results. So this talk may not be too advanced in an HPC standpoint, but it's an interesting mixture of seemingly unrelated fields, and maybe with some interesting results at the end. So I hope you'll enjoy. So my main research field is mechatronics and central data systems. And let's see this simple example. Because one of the main tasks of mechatronics is position control, and let's consider a single degree of freedom mechanical system, and we want to find a control input FU to drive this little cube to the zero position with the zero velocity in the presence of drive friction. And the drive friction is modeled by the Coulomb friction model. So most commonly we use closed loop control, and in this case we will use state feedback control. And every closed control loop consists of the plant, so the control system, and the controller in the feedback loop. This will be a digitally implemented control, so there will be a sampling and a holding subsystem in the loop. But the two main parts are the plant and the controller itself. So each of them has a corresponding equation. The plant has the equation of motion, and the controller has the control law, which is basically a linear combination of the state variables. So the control inputs, the control force consists of a term which is proportional to the position variable, and another term proportional to the velocity variable. The main challenge is in analysis of this kind of systems is the non-smooth dynamical properties, because there are two non-smooth properties. One stems from the friction model that we use. Drive friction, namely the Coulomb friction model, has a jump discontinuity because of the sign function. It depends on the sign of the velocity. And there is another non-smooth dynamical property, and this is because the sample data control. So at every sampling instance, the controller calculates a new control input, and this will mean another jump discontinuity. And the two non-smooth characteristics are resulting in a very special switch dynamic behavior, because the control is an equidistant switching behavior in time, but the motion reversals can occur between sampling instance And these two switching behavior is are independent from each other, making the analysis very difficult. So in order to a little bit in order to make the things a bit easier, we can use dimension analysis to reduce the number of parameters. So in this original problem, we have 5 parameters: the mass of the body, friction force, 2 control gains, and the sampling time. And by introducing dimensionless time, which is basically a time scale matching the sampling, we can reduce the parameters to 3. So there's P, D, which are control parameters, and the sigma parameter, which is proportional to the friction. Sample data systems are mostly considered in discrete time. So we can solve this equation. So we can solve the equation of motion between 2 sampling instances, and by assuming no motion reversal between the sampling instance, we can derive discrete time state equation. Basically, it's just a mapping which maps the current position and velocity to the next sampling instant. And this is a nonlinear mapping. As you can see, it consists of a linear part, which can be described by a matrix multiplication with this coefficient matrix A, and the nonlinear part, which depends on the sign of the velocity variable. And this contains the dry friction parameters. So it's not surprising that the dry friction will appear as a nonlinear property. So basically, this nonlinear state equation, discrete time state equation or mapping, can be examined in a special case with the frictionless system, and in the frictionless case, it simplifies to a simple linear mapping. Let's examine the properties of this linear mapping. So it's the easier case. So when the spectral radius of the coefficient matrix A is smaller than 1, that means that all the motions will settle, so the system behaves stable. But in the other case, when one of the eigenvalues is larger than 1 or is outside the unit circle, then the spectral radius of this matrix A will be greater than 1, and this means unstable behavior. So the system will explode in time. And this property will be very important later. So just jump to the next topic, iterated function systems. We will use iterated function systems to model this position control tasks. But at first, let's just talk about what exactly is an iterated function system. It's basically a finite set of functions, and usually these functions are contraction mappings on a metric space. I will talk about that later. And an iterated function set, or IFS, has a property that there exists a set X which has this property. So this might be a bit obscure at first glance, but this is a fractal property. It's a self-similar property. If you take this set S and use all of the mappings on it, then combine the images with union, that you will get back the same set. So it basically means self-similarity. But as you can see, this is an implicit equation. It's very hard to calculate this fractal set S. And taking the right-hand side of this equation, we could introduce a generator function called F. And if we apply this function iteratively on any non-empty set A, then as a limit, we can calculate the fractal set S. So this is the practical way of computing the fractal. And let's see an example to clear things up. So this is a fractal called Barnsley's Fern, this little nice creature here. And this iterative function system consists of 4 affine mappings. And this invariant set S is the whole structure here. And we apply all 4 of these mappings on the whole set S. And as you can see, we get smaller copies of the whole fractal structure shown in different colors in this picture. And by calculating the union of these 4 images, we get back the whole original fractal structure. So basically, this equation describes the self-similar property of fractals. So how can we use iterated function systems to describe the position-controlled system? It's very easy to see that the discrete time state equation of the system is just 2 affine mappings, and we can define an iterated function set with these 2 mappings, one which are only different in this nonlinear part here with the friction parameters. And the next question is, how do we calculate the corresponding fractal structure in this system? And this can be done by this generator function f that I talked about earlier. So basically, the original state equation mapped a position and velocity pair to the next sampling point, and we can use this to define the fractals generator function f, which does this on a set of initial points. So to calculate the fractal set S, we have to do the number crunching here, because in order to get high resolution picture, the initial set A must be very large, and we have to do a whole lot of iterations to get a clear picture. So I used OpenCL and the GPU to accelerate the computing of the generator function. And here you can see the implementation in kernel. It's very trivial. So we get the parameters p, d, sigma as arguments of this kernel function, calculate the matrices A and the vector A, and then apply the mapping. So let's see some simulation results. I use this parameter combination here, and this is particularly interesting because if you take these parameters and calculate this coefficient matrix, it has a spectral radius that is bigger than 1. So this mapping won't be contractive. Let's just jump back to the to Barnsley's Fern. We can see fractals usually are made with contraction mappings. So every little mapping will be a smaller copy of the original set, and in this case we see a non-contractive mapping. But if we start to evaluate the generator function to see the limit set, then we see that the system won't explode, and in fact there will be a very interesting fractal-like structure, and after 100,000 iterations you can see this fixed set here. So if we zoom in, we can see that the original set A, which is a circle with the two halves colored differently, has really the two halves are completely mixed up in a random manner. So this may suggest us, that chaotic behavior might be occurring here. And to further examine that, let's just start evaluating a very little initial set and see how it will evolve in time. And if we plot the distance between two closely initialized points in this state space, we can see that the distance is exponentially growing, which further indicates chaotic behavior. The trajectories are exponentially divergent, but this only goes for a certain amount of distance because there is a chaotic attractor in the center of this system. And by measuring the slope of this exponential separation, we can estimate the Lyapunov exponent, which is slightly positive, further indicating chaotic behavior. So in this little experiment, we analyzed a position control task in presence of right friction, and we consider this system as an iterative function system. We implemented the evaluation of the generator function of the system on GPU, and simulation results show chaotic behavior even when the mappings were non-contractive. So I hope you enjoyed this little talk, and feel free to ask any questions.
I don't see clearly what's prevent the system to see on the eigenvector, which has a larger than one eigenvalue, and it will grow forever. So what is probably I don't understand exactly what happens here. So why it doesn't grow, run away?
Maybe because this mapping, the linear part does a rotation on the points in that state space, and when this rotates to the other side, then the sign of the velocity will change, and the original state equation as seen here, then this non-linear part will change sign accordingly. So maybe this is why even when the linear part of this mapping is unstable, then the non-linear part will make this attractive behavior happening.
Fiction is it to say?
Yes, basically.
So really interesting. And last, if you have compared the control behavior and starting time and remaining error, compared the fictionless case.
We could easily calculate settling time and overshoot, for example, from the eigenvalues of the coefficient matrix, but in the focus of these simulations was this kind of attractive or stability behavior, and not the precise characteristics of the control.
Just another remark to the last question. The convergence angles you generalized values like the property of the function of the sign change.
Which one do you mean?
When someone mentioned why it is convergent, it's consistent despite it has a very normal spectral radius bigger than one. That's my understanding. This is a generalized variance.
Okay, I will look into that, but I'm not familiar with this property, so thanks for the remark.
Let's thank the speaker again.
Next speaker will be Gábor Dániel Balogh, who will talk about family disorder.
So, hello everyone. My name is Gábor Dániel Balogh, and I'm a PhD student at Pázmány Péter Catholic University. My supervisor is István Reguli, and with the help of Zoltán Juhász, in the last year, we worked on a scalable batch pentadiagonal solver library. So basically, in this talk, I will show you a bit around the pentadiagonal systems and different solving approaches to them, and basically show our design considerations to create a scalable library. And finally, I will show some performance results on the LUMI supercomputer. So this talk will be a bit familiar to some of you because István gave a talk on the tri-diagonal solver library that we made in 2021. And basically this work is just the follow-up to that work, trying to provide more flexibility and accuracy for CFD applications with pentadiagonal solvers as well. So pentadiagonal equation basically is just a traditional system of linear equations where you have non-zeros on the main and two lower and upper subdiagonals. So to solve such a system, the first idea that comes to mind is using Gauss-Jordan elimination or a specialized form like the Thomas algorithm, where you eliminate the lower subdiagonals first in a single pass, and then you can have a second pass eliminating the upper subdiagonals. But this is a sequential algorithm. And if you want to use parallel algorithms to solve a single pentadiagonal system, you basically have two choices. Go with something like parallel cyclic reduction for pentadiagonal systems, where the idea of PCR is basically you push the subdiagonals away from the main diagonal at each iteration, basically dividing the equation system into two independent equation systems at each iteration until you have the solution, which will give you a log n sequential steps, and at each step you have n parallel steps. And what we did, so for pentadiagonal systems, you can take two approaches with PCR, either using the PCR penta, where you keep the equation system in the pentadiagonal form, or you can transform your equation system into a tri-diagonal-like structure of 2x2 blocks, and which will make your PCR shifting to a more compact communication, which I will show when we talk about the MPI communication we have. The other approach that you have is to use some sort of hybrid algorithm, where you divide your equation system into partitions. You have independent work as a first step in each partition, forming a reduced system. We show it here with the ball, if you can see it. So basically the first two equation and the last two equation within each partition will form a new reduced equation system that you can solve, and then when you have the solution for those equations, you can use back substitution in parallel again. So we now know how to solve a single pentadiagonal system, but we don't really aim to solve a single one, but we try to give support for alternating direction implicit methods. Like, for example, flow solvers based on implicit high order finite difference schemes, where you want to solve a pentadiagonal system along one dimension at a time, and you have your coefficients and unknowns in a 3D mesh. Moreover, your 3D mesh is decomposed at every direction between your GPUs. So you don't have access to the whole equation system at the time. So for this, we chose the hybrid approach. So we create the reduced system at the first step, and then we have to solve this distributed reduced system in the second step, and then we have the back substitution step again. To solve the reduced system, you have basically free choice to use some sort of gather operation to gather the whole reduced system to one node, which basically doesn't scale, so we didn't really do that. And the other two approaches is to use an exact solver, a PCR variant, where you have one-to-one communications between the ranks, but the communication distance is increasing with the number of nodes you have at each iteration. And the final one is using an approximate solution with the Jacobi iterations, where you have local communication, but you might end up with more messages than with a PCR. So to walk you through the whole algorithm, first you start with your pentadiagonal system, and then you run your forward pass to form, in our case, the 2x2 blocks and the reduced system at the borders of the partitions. Then you have one more reduction step to eliminate another two equations from each partition. So you end up with basically the first two lines at each partition will form your reduced system. And with these equations, you have a reduced solve, and then again, back substitution. So what we want to highlight is the difference between the two approaches of the Jacobi iterations and the communication pattern there and the PCR iterations. So in the case of Jacobi iterations, basically your communication pattern doesn't change at all between the iterations. You always talk to the next process and the previous process, and that's all. But for PCR iterations, you have to communicate with processes with increasing distance between. So we will see the communication cost difference between the two approaches. And now I will show you a few performance scaling results on the LUMI supercomputer. And the main numbers to keep in mind is that LUMI has 4 AMD MI250X per node, which means you have 8 GPUs in a single node with a fast interconnect. And we set up our measurements that all GPUs are positioned in the solving direction, since the algorithms scale trivially in the other directions. and we fixed the Jacobi iteration count to 10 to really highlight the difference between the two approaches. So the only cost that defines your scaling is the distributed reduced solve. So for the first try, on your on the right, you can see the like weak scaling performance of both the Jacobi and the PCR algorithms that we use. At first, naively, we tried to just the simplest solution, copy everything to host, do MPI communication on the host, and copy everything back, which, as you can see, doesn't scale at all. So we had to switch to GPU Direct, which has really great performance on Lumi. And from that point on, the interesting thing that you can see on this chart is that at the bottom with blue, the GPU Direct with Jacobi, you see performance bumps, but we always have 10 iterations of the Jacobi iterations. So each performance bump comes at when you cross a border in the Lumi hierarchy. So you have a bump from 2 GPUs to 4 GPUs because you use 2 MI250s. Then you don't have any change between 4 and 8, and you have another bump when you cross the border of a single Lumi node. And from that point on, the performance of the Jacobi solve basically stays exactly the same, except for whatever reason, 512 was an outlier. And compared to that, the PCR iterations have fewer iterations up until basically 1,000 GPUs, where we have 10 iterations as well. But the cost of each iteration will increase. So we can see the cost here as well clearly, that each iteration takes less time until we are within a single Lumi node, and after that we have the same communication cost increase at each step. So these exact numbers will determine the scaling performance, both in strong scaling when it comes to the whole solve, and both in weak scaling. So for strong scaling, we scale the 1,000 equations long equation system from 1 GPU to 64 GPU, and you can see that the performance gain from reducing the system size and doing more work in parallel at the first step balance out the increasing communication costs up until the 8 GPU mark, where you basically have 2 small kernels, and the communication of the PCR at least will define your runtime. And for weak scaling, basically we have similar results. We see the same pattern. We have the same increases, and the Jacobi can keep up the performance since the communication does not change, and there is the steady adding climb of the PCR iterations to end up. So in conclusions, we created a parallel distributed pentadiagonal system solver library, and we run the scaling experience on Lumi, and maybe the biggest takeaways that can be applied basically everywhere when you work on Lumi is to know your hardware, know where you crossing boundaries of communication, and try to keep your communication, if you can, within the hierarchy that the hardware that you run on. And basically, another interesting thing is that basically don't have increase in the cost of communication after 16 GPUs in Lumi. What I mean is, if you communicate one-to-one between two GPUs and you are outside of the border of the Lumi node, then basically you have a constant factor that you have for your communication. And thank you for your attention.
Thank you for your presentation. I have a question, maybe not about the performance, but about the numerical correctness or the precision, because I have some experience for the tridiagonal system solver. And actually, we designed our own kernel functions to solve the tridiagonal system because we want to perform some kernel fusion instead of just using the Q solver provided by the CUDA framework. But we found that for the smaller size system, like less than 100 dimension tridiagonal system, the result is quite okay. But if we extend to 1,000, even 10,000 dimensions tridiagonal system, the numerical correctness will be a problem because it will produce totally different results. I don't know whether you have any numerical validation on your penta-diagonal system solver, or have you ever met similar problems before?
With the Jacob iterations, you definitely have this problem, of course. It's an approximate solution. With the PCR, as far as we tested, we didn't see a big problem in accuracy with the PCR iterations.
So the biggest dimension of the tridiagonal system you tested is 1,000, or?
We tested, like, I think we ran tests up to 1,000 for the penta, and I think we had bigger tests for tridiagonal. But yeah, I'm happy to check on that later, and we can talk about it.
Okay, no problem. Thank you so much.
Thank you. Thank you.
So when you describe the hybrid solver that you used, it resembled a lot to the spike algorithm. I don't know if you came across that.
Yeah, at one point for the tridiagonal, I think for the tridiagonal.
Yes, I came across the spike algorithm using the tridiagonal system,
Yeah.
but it is supposed to work for any band.
Yes, yes. I know that it exists, but I haven't implemented or played with it yet. So I'm not really sure. But yeah.
The stuff that I resemble that a lot, and I cannot say that they are the same because when I came across it, I had one embarrassingly large system that I had to solve, and that seemed to be the ideal choice.
Yes.
I didn't have a batch of systems to solve, so the requirements are slightly different. Very likely that the solutions are different.
Again, I think for the tridiagonal case, we came across multiple algorithms that basically was a variation on the same theme. So this divide and conquer main steps are basically the same for a lot of algorithms. So maybe the exact details on how to create the reused system and such is the key difference. Yeah, thank you.
If there are no more questions, let's thank the speaker again.
Thank you.
And I call our next speaker, who will be Balázs, and he will talk about AI-driven stellar aspects.
I think like result.
I'm devoicing.
Going. So.
Can you hear me? Okay, can you hear me now? Yes. Just give me a second. Okay, I hope you can hear me now. I'm okay. Okay, that's great. So thank you everyone who stayed here at the for this last section. I know everyone is tired, so I try to not tell you a bedtime story. So I will be fast and be probably a good presenter. So my name is Balázs Pál. I'm a PhD student at the Eötvös Loránd University studying physics. And well, I do many things that's related to scientific computing. I'm also doing my cooperative doctoral program here at the Wigner Research Center with Gergely Barnaföldi, a name you could probably heard before, and with István Csabai, also a name you probably heard before. But in the past couple of months, I had the opportunity to work with a research group at the Johns Hopkins University, and they call the PFS Galactic Archaeology Team. This is a smaller international collaboration that's primarily focused on doing research with a new instrument of the Japanese Subaru telescope at Hawaii called the Prime Focus Spectrograph, or PFS for short. And I would like to tell you about this research, or what I did in this project exactly. But before I talk about the actual research, let me tell you about the motivation or the scientific rationale behind it, because I think it's very intriguing and I would like to tell about this. So there is a very well-known model in physics that everyone who's related to physics in some way heard about. Is the standard model in particle physics with capital S and M. And for those who are not physicists in the audience, it's just basically a physical model that tries to explain a huge domain of phenomena in particle physics. But it is, I think it's much less known, but cosmology, the large-scale study of the universe, also has its own cosmological model that intends to describe yet another domain of phenomena, which in this case is related to the structure and the long-term evolution of the universe. And that is currently called as the lambda CDM model, but it's much less established than the standard model in particle physics. Why is that? In the past couple of decades, let's say maybe 30 years, several different problems of this model arise that question its accuracy in various topics and even its validity in general. It's still considered to be the so-called standard model of cosmology. However, its problems are indisputably widespread and needs to be addressed somehow. And because since it's such a huge field in physics, we have quite a large amount of different ways we can address the various challenges that the lambda CDM has to face. And some of these ways are more direct, some of these ways are, well, less direct, and they consist of a stepwise approach to these different problems. And I had the chance to work on one of the myriads of approaches, and even in that, my work consisted just a single step of the bigger picture.
and it was a single cog in the entire machine. So what is this approach in particular? It is, as the title says, it's galactic archaeology using the Subaru PFS instrument. Galactic archaeology, well, first of all, I think it's a funny name, because when I say archaeology, what you think of, I don't know, dinosaurs and ancient cities buried down, deep down in the ground. And funny name or not, it describes really well what this approach is all about. All the past events and processes that shaped our galaxy left some marks on the stellar attributes of stars inside our galaxy. And by stellar attributes, I mean like the chemical composition or spatial distribution or dynamics of the stars in the galaxy. And using these clues imprinted on stars inside our galaxy, we can infer how our galaxy evolved over the past couple billion years. And with a better understanding of galactic evolution, we can constrain the nature of the effects that originally influenced it in the first place and created this galaxy. For example, what kind of things I mean, like influenced it, for example, the dark matter distribution in the universe, or the exact halo profiles of our galaxy, or the halo profiles of the satellite galaxies of the Milky Way. Successfully constraining these, well, peculiar phenomena is not enough to solve the problems in cosmology, but will be a step closer to a more accurate and a valid cosmological standard model. Okay, but these are many consecutive steps that should be taken by several research groups over a span of several years. And the PFS Galactic Archaeology team is involved in the first phase or first step of this flow chart, namely the examination of stars and stellar attributes and the observation of these, not just the examination. And the best tool we have at our disposal to accurately measure these relevant stellar attributes is spectroscopy. And I can mention two simple reasons why this PFS instrument on this Subaru telescope is important enough or interesting enough to have an entire collaboration formed around it and do spectroscopy with this exact instrument. First, the Subaru telescope is the best ground-based telescope on Earth, period. This telescope itself is capable of wide field observation, which just means that there are many stellar objects inside the field of view of the telescope at the same time. The second reason is that this PFS instrument is designed to be able to simultaneously and rapidly collect a large number of targets in the telescope's field of view with like a fairly good accuracy. And these two instruments combined will provide us a large number of spectroscopic data in the future. Yes, you heard, only in the future, since we don't have real spectroscopic data yet. So we were working with synthetic stellar spectra in the meantime to develop the pipelines that will be used in the future to analyze the observational data once they are ready. Now, how accurately you can simulate or these synthetic spectra is another topic on its own, so I won't speak about that. The only thing I will mention is that that we already have the necessary software to generate pretty good artificial spectra, at least for the parameter range that this PFS instrument will collect data from. And on this slide here, you can see how these synthetic spectra look like. They basically consist of two main parts. The first part is the stellar spectrum itself, which is generated from some kind of stellar model. And the second part is the noise, which is generated from some form of noise model. Of course, this software capable of doing other things with the spectra, but the exact the spectra I was working with consists of just these two parts. So there's anything in these. And on this figure, you can see like the blue lines and the gray lines visualizes the noisy spectra. And just as a comparison, the pure spectra is represented without any noise as the orange and the white lines. And these are just for visual purposes, it's here. Okay, but what exactly can we do with data like this? We have countless options. So what we were actually interested in out of this plethora of choices. We wanted to see how deep learning methods are able to tackle the different questions that's related to stellar spectra. Of course, everyone's doing machine learning and AI nowadays for practically everything, sometimes even without any thoughtful consideration. But in this case, you will see that why we thought that machine learning or deep learning methods could help us analyzing this data. So we first compiled a list of questions that we wanted to answer and try to come up with the most appropriate deep learning method or machine learning method for them. The main question we wanted to answer at all of this project or at the part I was working on, that how or can a deep neural network the noise spectra I just shown you before. So can a deep neural network subtract that noise and reconstruct the original spectra from observational data? Why is that necessary? Obviously, observational data will be noisy. Unfortunately, we can't do anything about it. But it would be great if an AI could just subtract that noise on the flip of a switch. That would be really great. The reason why we want to do that is not obvious. So, I mean, of course, you can say that noiseless data is almost always better than noisy data. That's okay. But I can mention two exact practical reasons why we want to do that. One, that the actual existing methods for the determination of stellar parameters involves a very annoying step, and that is continuum normalization. And continuum normalization is basically you have to find the blackbody continuum of a stellar spectra. On this blackbody continuum sits the emission lines and the absorption lines and things like that. And you have to subtract it from this measured data. And from that, you can use different methods to determine the stellar parameters. However, in case of if the noise is big enough, this is basically impossible to do. So it would be great if we could just efficiently and accurately subtract this noise from the spectra, and then we could use the normal classical tested methods to determine the stellar parameters. That's one thing. The second thing, that there is an extremely important and very annoying technical detail behind a huge portion of scientific experiments, and that is that researchers, research group, institutions, or sponsors have to pay a lot of money to use telescopes, to use computing clusters, to use hadron colliders. I don't know, you know it, you name it. And in case of astronomical observations, what happens is that you create very long exposure observations to collect as many data and of your stellar objects, and to increase your signal to noise ratio as much as possible. However, it would be really great if we could tell the details about these different observational targets, even in low signal to noise conditions, and then we could just spend much less time and money on different measurements. That's a use case, for example, here. So it saves a lot of time and money, and also assists these classical methods I just mentioned. Okay, but the very first questions before that we wanted to answer, just to test if AI is really a walkable path here, is that whether we can encode a stellar spectra or a stellar spectrum to some low dimensional embedding and then reconstruct it from that embedding. And in simpler terms saying, if a deep neural network looks at the stellar spectrum, can it like encode it to some small number of parameters, and that from the small number of parameters can we somehow reconstruct the original spectrum? That was the test case that we tested before. So it was obvious to us at this point that we have to use some form of autoencoder network, which is like used, which has like it has an immense amount of use cases nowadays. What it does, its so-called encoder side basically performs a dimensionality reduction on some form of input data, and the decoder part tries to reconstruct that original data from this low dimensional representation. And this is basically what we want to do. This is just I said like a couple of seconds ago what we want to do with stellar spectra. And we try to use an autoencoder model. And after building this model and training it on synthesized data, we concluded that it worked much better than we expected beforehand. In this case, what happened is that we put the original pure noiseless spectra to the encoder input, and we trained it in a way that the decoder side would be as similar to the original input as possible. This is by default what an autoencoder does. And you can see the results on this slide. The top panel shows just a random spectrum selected from the data set, and its reconstructed counterpart overimposed on this image. You can basically see no difference. That is just one line, and it means that the input and the reconstruction is overlapped. So the reconstruction is pretty great. And that's why I have the bottom panel, which shows the relative errors of this reconstruction. And the only interesting thing that you should see here, that the errors are large where the large absorption lines are located. And this means that the autoencoder has the hardest time reconstructing the exact size of these emission or absorption lines. Okay, we had many smaller and larger problems during this project. So we are really happy to see the results that I showed you. So it gave us a lot of motivation to continue the project and see whether if it can tackle the original question, can it really denoise a network or a spectrum and reconstruct the pure noiseless spectrum from that noisy data. And in this particular case, the input to this autoencoder network was just a noisy spectrum that you can see on the top panel. And it has very strange colors compared to my screen, but it's okay. So the input was this noisy spectra, and on the decoder side at the output, we expected the true noiseless spectra, and that's how we tried to train this network. And you can see the results of this training here. You can see also the middle panel and the bottom panel are the same as before. They are on the bottom, on the middle panel, you can see that the reconstruction and the original model is quite much overlap. If you come close and look closer, you can see the differences, but you can also see the differences on the bottom panel. And we can see the same thing here, that even though you can see like 15% relative errors and the same thing that before, that the model has problems learning these absorption lines. This was really these results are really good, since the continuum of the spectrum was found, and even the emission lines were found at the location, and the approximate size of the emission lines were found by this autoencoder network. So how to continue this? The goal we aim to reach is to reproduce or even surpass the results using a model that an autoencoder model that has convolutional layers, convolutional blocks instead of simple dense layers like we had before. We have already some preliminary results, and if you look up the literature, people try to do things like that. So what others try to do, what you can find articles about it, that they try to infer the actual stellar parameters using convolutional neural networks from a stellar spectra. They also use synthetic spectra, but noiseless spectra. And that's one thing we want to do. And the other very important thing that these models, or so spectroscopy, we don't always do on stars, but we sometimes do it on galaxies. And in more distant galaxies, there is a, well, it's an annoying thing that the spectrum or the photons coming from them redshift pretty much. And it's said that convolution autoencoders are usually like translation invariant, and they could work better for data sets that have like heavily redshifted spectrums, because like what translation happens here, that due to the photon undergoing redshifting, the spectrum is just translates along the wavelength axis basically, and it probably convolutional autoencoders could probably solve that issue, solve the errors arising from this translation. So time will tell that if we are able to tackle these challenges, but that's the end of my presentation, and thank you for your attention.
Yeah, thanks for a very nice summary of this research. So one of the questions which put into my mind is how can you, what are the ways you can the real noisy spectrum to be, let's say, generated one or something like that. So do you have, can the AI pick up the noise at a certain level? Can you quantify this somehow? So what apart from simple correlation, what is the quantitative things?
Quantitative, nothing really. I am not sure if I understood correctly your question, what it refers to, but like what we do is, in case of autoencoders, we input the noisy spectra that has some noise. We don't really care what the properties of that noise, and on the decoder we input as a target the original noiseless spectrum.
Yeah, which is very much model dependent. Yeah.
Yes.
So that's the question. So how you can really decompose the model dependence in the not the main peaks, but in the context part and the noise. So if you were able to recognize the noise patterns, like if it would be a simple gray noise or limited white noise or whatever, then you can decompose or at least you know some properties of this. But if you have a very model dependent one that is not an easy task, and I know that's the just thinking.
Yeah, I don't know. I don't know how to answer really, but okay, that's an interesting question. Yeah, like we know exactly what noise we put on these models. That's basically deterministic. You can say that. So I don't know. I don't know what to answer, but okay.
I just have a very late question. Why did you choose not to include any dropouts for normalization?
Well, we included dropouts and normalization. So dropouts, because like the networks learned much slower because of them, and they didn't produce better results. We did not include batch normalization because the models we had even a worse or worse results than with batch normalization than without batch normalization. I don't know the reason for that. There were some like brainstorming, why is that and why batch normalization doesn't work in case of these type of data, but we concluded that we shouldn't use that because it doesn't work. That's why.
How many parameters had you in the bottleneck of the variational encoder?
simple autoencoder. Well, I tested many different number of parameters in the latent space. I even had models that, for example, these figures, where is that? So these figures were generated with a latent space of where there were 64 neurons in the latent space.
Because things that is the information which is transferred through the autoencoder. So it somehow should correspond to the peaks you can find.
No, so optimally, we can have as many latent or latent neurons in the latent space, as many physical parameters. So physical parameters obviously determine how this spectrum looks, and we can go down as much as many physical parameters we have theoretically.
But these are the peaks.
I'm not sure if these are peaks, but probably. I mean, the physical parameters like the effective temperature and the surface gravity of the star and things like that. And yes, the chemical composition also. The problem is that we. So the problem is that we don't really have perfect stellar models. We have different stellar models. We don't really know this is still a very unknown area in physics that how to model exactly a star. What are really the relevant physical parameters? It is an open question.
There is no more question, then let's let the speaker in. And our next speaker is George Kishander, who will talk about heuristic optimization at protein investigation.
Okay, I hope my bird don't insulate the microphone too much. Welcome everyone. I'm George Kishander from University of Pécs, Department of Engineering, and I would start by renaming my presentation. This is a really fancy name, but my aim is to give you a little bit of inspiration to use your favorite AI frameworks for other than AI purposes. So we can call this as using AI frameworks for non-AI problems.
You just click on the screen, right?
Oh, for sure. Okay, why? First of all, I work mostly as an electrical engineer and a data analyst, so I have lots of data to analyze, lots of computational tasks, but not always machine learning or AI related. And I got bored and overcrowded with different frameworks for different problems, like the control system toolbox for control systems engineering, or a SPSS for statistical data analysis, and so on. And I tried to gather all my daily tasks and solve them with one single framework. So I don't have to learn lots of different frameworks. Okay, AI frameworks. In the last 2 days, we saw lots of nice presentations and AI applications based on the current popular frameworks. And this is just a historical chart on their appearance. I think nowadays two popular frameworks are the TensorFlow and PyTorch. So basically, I think 99% of AI applications based on these two. But also I think most of you met with the others. So my favorite one that I use most is PyTorch. The main reason is its imperative style. I started with Keras and TensorFlow and so on, but I found it somewhat hard to implement even really easy mathematical or computational problems. So I stuck with Torch because it's really intuitive and it's almost a drop-in replacement for NumPy. Okay, here we can see the typical architecture of an AI framework. At the bottom, we have our computation hardware, of course, CPU, but less and less common to do AI on CPUs, and some AI accelerator, like GPUs, TPUs, FPGAs, and so on. Each of them have some hardware-specific library that can be used to implement our mathematical models. But also I'm too lazy to learn all the different hardware-specific libraries. So I moved in the upper layers in this stack to the top. Basically, the TensorFlow, PyTorch, and so on, high-level AI and ML libraries. There, we still have access to elementary mathematical operations, but with them, we also have access to some more complicated algorithms. So it's really easy to construct a computation using these frameworks functions. Okay, so this is the main reason I like to use, or the second main reason, I like to use AI frameworks for hardware accelerated computations that they provide uniform API, basically independent from the underlying hardware. So even if we use a laptop with a dual-core CPU or a full cloud or cluster, we have the very same API to solve our problem. So again, we don't have to memorize the vendor-specific codes. Also, if we want to move our code from one platform to other, it's basically platform independent. So if we create a Jupyter notebook or so on our workstation, we can run it as it is on a cloud platform. Okay, my favorite part, my next favorite part is the auto-bit and auto-gradient modules in these frameworks, especially the PyTorch AutoGrad. The AutoGrad serves as the basis for the training algorithm for neural network, the backpropagation. Some of you already mentioned backpropagation algorithm today. It's basically the training method for neural networks. Next to this, usually we solve neural network training problems with some gradient descent algorithm. And behind this gradient descent, we have access to the AutoGrad module that can calculate the gradient for any computational graph that is defined within the AI framework. And if we have AutoGradient, then we can basically do a minimization task or something on that computational model. Okay, so really easy computational graph.
I think you get recognize it. This is just one artificial neuron. We have X as the input, W as the synaptic weights of the neuron. Then we have a bias parameter and some non-linearity, like a rectified linearity, something like this, or sigmoid. Then, if this is a supervised training problem, we have Y the correct output for the X actual input. At the end, we have loss function that measures the difference between the correct input and the guess of our learning algorithm. And by using the autograd module, we can calculate the gradients of this loss function with respect to the model X parameters. Okay, so motivation summary. We have high-level abstraction over different vendor-specific mathematical libraries, uniform. These tools, functions, modules are not restricted to ML and AI applications. So if we can formulate a problem using this, then we can solve this within this framework. Then we can solve non-AI problems using AI hardware acceleration. Okay, and my example is graph coloring. It's a really silly idea. Its origin is that I walked into a pub, and maybe you remember that a few years ago there was a political campaign to for color the sidewalks. So I saw this four-colored sidewalk, and I had the idea to solve this by using an AI framework. So what is for coloring? In a loopless planar graph, we need at most 4 colors to color each vertices. So no two neighbors will have the same color. In the example, I will use the United States and not all the states, because I will on Alaska and Hawaii. Why? Because they share no border with any other states. Also, in my baseline example, they are 50. So the problem is to color the states of US with 4 different colors. To do this in this AI formulation, we only need the adjacency matrix of the states. Also, I stole the states graph from the internet, and this is just the adjacency matrix that I created for the states problem formulation. As a start, I told you we need the adjacency and we need another matrix that will contain the coloring. This coloring matrix will have as many rows as many states. So in our case, 48 maybe by omitting the last and and 4 columns. Because each row will be a one-hot encoded vector for a given color. Initially, we fill this color matrix with random numbers and apply a softbox norm by each row. This will force one-hot encoding during the training or session. Okay, so that's for the start, and as the result, I want to have really nice one-hot encoded perfect color representation. As you can see, we have this backward flag here. This means that this tensor can be modified with the autograd module of Torch. Okay, so initially with random colors, the coloring looks like this. Basically, this is some kind of a superposition of the 4 colors, and each state has some random. Okay, next we need a loss function or an objective function to solve the problem. To do this, we basically calculate the gram matrix of the color vectors. So we have a state-by-state square matrix where each element is or can be interpreted as a similarity between 2 states colors. Simple dot product. Okay, next we mask this similarity matrix with the adjacency matrix. So we drop the non-neighboring similarities because we don't care if 2 non-neighboring states are similar in their color. After that, we sum reduce all of this to have single numbers. So we now we have a scalar valued function, and its parameters are the color vectors. Also, A is a constant because we don't move states during the optimization. Okay, coding. It's a really silly few liner. So we only have to, I use the NN module, but it's unnecessary. So we just use a random tensor that requires gradient. So we want to optimize this for Torch module. We have to define forward pass, like evaluating the computational graph. And we can have other functions that we can use during the optimization. Here, the reduce T is just the tuning for the one encoding. So by changing the value of this parameter T, we can change the convergence rate during optimization. It's not learning rate, but it works in somewhat tandem if you use it. Okay, next, our loss function is that short formula that we saw before. And the training loop. I call this training loop because this really looks like the training loop of a neural network. So in the forward step, we just evaluate the loss function. CC contains our coloring value. Then 0 with the gradients, and with the backward step, we modify the color vectors, and we continue this after our loss hits some acceptable level. That's my 0. It's a relatively huge number, but due to numerical stability, I like to use something like this. Okay, with this heuristic nature, it won't converge all the time. So we have to implement some restart conditions when we recreate all the coloring with new random colors and so on. Also, in my experience, I used the Adam optimizer Noy. The model converged after 1 or 2 restarts, so it's not so bad. Okay, results. I hope you won't find any errors in this. I just saved math with some nice loss value. I used the Jupyter Notebooks time it magic function to measure some basic timing, and I tried to run this model on some different devices. This algorithm was run on the listed devices like the i5 CPU, an old, somewhat mid-range GPU, and a cloud Tesla GPU. And as the baseline, I use DWaveLeaks CQM solver to get some really fast and nice result. It uses a different algorithm, of course. Okay, and the timings. As you guys, I think the CPU was the slowest, but it brought this speed at some constant rate, so 24 seconds is not so bad. Then the old and mid-range GPU, and I think this is interesting that the Tesla huge GPU not improve the runtime so much. Also, it had huge fluctuations in the runtime. I think this is because I used an on-demand solution, so I got free GPUs when they were available. And for the deep QP, you can see that it's much faster, still much faster. But if we consider the pricing, then maybe it's not worth to use quantum computing to solve a silly problem like this. Okay, so some conclusions and remarks. AI frameworks can be used to solve any computational problem if we can formulate them within the framework. I can recommend PyTorch to do this. Also, if we have a solution for our problem, then we can scale it of different hardwares without modifying a single line of code. It's easy, so moving computation between CPU and GPU doesn't require CUDA knowledge or something. It's just an argument to use GPU, please. And some additional remarks on the example. Future goals. I want to compare the algorithm with some other well-known algorithms like Greedy and so on. So later I will have some more precise results on the efficiency of solving such a task in an AI framework. And next to this, so graph crawling was just an example. I use it regularly to solve other tasks, so filter design, even for, I have an example for Fourier series calculation when I calculate the coefficients with SGD. So it's really flexible for our computational problems. And thank you for your attention.
A remark that maybe for few parameters like here, Adam maybe not the best solution. Conjugate gradient may be faster, but we should try. The question is that did you try it in other topologies? So it was a flat topology, so in sphere or in torus, it would be the
no, I only tried it on countries. So the other data set was Hungarian counties, or I don't know what's the English for Vármegye. But only for states, counties, countries, and so on.
So if you try it on sphere or torus, the four colors, so you need person easy one to reveal that how this program can reproduce that.
Thank you. This sounds like a good idea. Thank you. Yes, I just wanted to congratulate you on the talk. I really like the premise of using something where it wasn't meant to use and not having to learn too many frameworks. I just wanted to suggest an unsolved real world problem that I happen to know that which exists. It's finding timetables for classes and teachers with various constraints, like somebody only wants to come in on Fridays, or they never want to have class before 9 o'clock, something like that, and assign teachers to classes, to classrooms. And that is an unsolved problem, and I believe it could be used in similar fashion to solve using machine learning, find an optimum or at least a minimum to some of the finds. Yeah, thank you. It flows a little bit because I'm the head of the electrical engineering program at University of Pécs, so it's my task to do the. I think it's such a tool to do this. Also, it's a nice constraint problem. So yeah, I consider this. Thank you.
Okay, there is no more question, then that's that. Yeah.
And our last speaker of this session will be Mira Gergác, right? She's the last. And in her talk, she will take us apart.
So, good afternoon, everyone. I'm here with a rather topical presentation compared to the ones we've been hearing in the past couple of days. But I'm hoping it will spark interest. I'm Mira Gergác, a student of the Ötvös University. And yes, will be trying to analyze high resolution digital images on Mars. Now, the search for ephemeral liquid water on the surface of Mars is an ongoing activity. And in my bachelor thesis, I'm trying to join in that search, looking for an answer to the question whether Martian water ice can remain in warmer temperatures. It might be possible due to the low thermal conductivity on the Martian surface and the atmosphere, because during the seasonal recession of the polar ice caps, smaller water ice patches can remain in shaded areas, like behind rocks or in craters. And these water ice patches might warm up rapidly when they are met with direct sunlight in or during a southern spring or summer. And as such, melting emerges as a possibility. Now, the melting point of water ice on Mars is 273 kelvins, while the stable temperature is around 200 kelvins. So normally water ice sublimates before it could reach the desired temperature. However, in theory, if this temperature rise happens quickly enough, melting might occur. Here's an image of the Martian frost, It's in the northern hemisphere, but so it's there, it's real. The methods we've been using with Ákos Keresztúri were technically looking at images that were made by the high-res camera on board of the Mars Reconnaissance Orbiter. This camera makes very high resolution images, as you can see, 0.3 meters per pixel. For a comparison, Google Earth can reach 0.15 meters per pixel. So it's pretty good. You can see a lot of details on the surface. Now, there are 1,400 available images in our selection criteria, which means that we are looking at images during the southern spring when this recession occurs. Now, we've analyzed 110 images and 37 had smaller ice patches on them. These images were analyzed manually, which means that we've been looking at them on the screen, scrolling to the images and looking for bright patches that were essentially recognized by their strong connection to the local topographic shading and by their color. Here is the MRO, or Mars Reconnaissance Orbiter with the high-res camera on board. Now, after we analyze these images, we run down simulations using the Mars Climate Database. We were simulating average noon temperatures and the predicted CO2 and H2O ice coverage. The problem with this was that it only gives a general information on the area temperature-wise. It's not suitable for detecting small temperature fluctuations. Here are a few examples. As you can see in RGB images, the ice is pretty, it stands out, right? It's white, surface is reddish color, it's easy to identify them. Now, our first results were that these ice patches are distinguishable from other bright areas. They range between 140 and 200 degrees in solar longitude, and in the latitude band between -40 and -60 degrees. They remain for about 19 and 133 Martian days on the surface. Sadly, judging by the temperature simulations, the occurrence of liquid water on the macroscopic scale is highly unlikely. However, as an interfacial pre-melting of ice might form, which is essentially a few nanometers thick liquid water between the ice and the layer. And if it emerges, it might influence low temperature chemical changes on Mars. Now, this is great, but we want to work with more data. You can see we were working with very few images, and analyzing these images is very time consuming. You know, there are these high resolution, huge images. They range in size, but on average, they are 15,000 times 30,000 pixels. So it's very time consuming to look through them. And here is where using a neural network comes in. Because our problem is similar to the cat and dog case. We have two types of images that we want to distinguish between, one that has small icy patches in them and one that has none. So these high-res images need to be collected and organized into two groups. The program will learn the difference between the two groups and will be able to recognize ice patches on images it has not seen before, once the training is successfully done. And the advantages are evident, but still I would like to point out a few.
on one hand, it will become a realistic goal to analyze all available surface images, since the search will be automatized and time efficient. Also, the search will be more throughout. I'm hoping that a CNN might be more effective in identifying ice in black and white images, because the contrast can be very little on black and white images, especially if the surface is already in a lighter shade. It's very hard to detect a white patch. Also, it scans the whole image, so no ice patch will go undetected. First, I had to prepare the data, which mostly consisted of increasing the data set, since 34 images is used for training, but even the 110 that we analyzed is not enough for a CNN. Each of these images were cut into hundreds of chunks, creating over 6,000 images, which is a much more better size of data set. 42% of the images have small icy patches on them, and the rest shows none for CO2 ice sublimation on the surface. And CO2 ice sublimation is not good for us either, because we are looking for ice patches that can be directly met by sunlight, which is not possible if CO2 ice is still covering the surface. I left the image size a bit large, but it's important because the surface elements are important as well. It's not enough for us to just detect a white patch on the surface. It could be a rock or anything else. Now, here is what the neural network works like. I was using a small version of Exception Network by Colette. There is the source for it. I will be running it in a batch size of 30 with 25 epochs and a 0.5 dropout rate. 20% of these images, or the 6,000 images, will be used for validation. And yes, it has an Adam optimizer and 2.7 million trainable parameters. Since the training has not been conducted yet, I don't have any results, but I'm very hopeful that it will aid us in looking for areas that we can further investigate, possibly find some kind of melting of water ice on the surface. The data is uniformized, the data set expanded to a sufficient size, and what's left is training and testing the model for now. Yes, thank you for your attention.
How do you make a distinction between CO2 ice and water ice by eye? So what is the difference?
Luckily, CO2 ice is transparent, so only water ice appears as a white patch on the surface. Technically, this is.
So, what is the real size of such an image? So it's how many meters by how many meters? And the size, and also the size of the ice.
Yeah, these images have a scale on them, since the size of the image varies. I can't tell it for sure, but most of the ice patches that we detected range from 5 meters to, I think, 130 meters in diameter.
Is there a way to distinguish the methods part and the part on the ice?
By eye, sadly, there is no way to do that. But if we successfully map the given area, it might be used for expeditions in the future. And yes, rovers can go there and inspect the site.
There are no more questions. That's time. In summary.
Yeah, just sort of like this. No, you can. Okay, so we are at the end. And let me just very briefly summarize what happened in the last 2 days. So first of all, let me thank you very much the support which is coming from the big Hungarian Academy of Sciences, the Ötös-Loránd Research Society, the Lobbyk Limited, who is not here anymore, but the Stream HPC, Mate, they present and with 2 other colleagues. So thank you very much to be here, and hopefully next time not only Mate will speak. The Quantum Information National Laboratory in Hungary and the NLD office, who are all for us. And you know, maybe you remember my slide in the first day that what AI is thinking on the GPU days. So maybe let me put this to a more human readable format. So this is, you know, this word cloud, and as you see, the main use the GPU laboratories webpage or VSC webpage to dig out this data. And you see the GPU is of course here, the quantum is also here, and the physics is also here, and some other topics. Actually, there are a couple of names. Balázs is also a very frequent name in the laboratory. Everybody Balázs. So raise your hand if you are Balázs. So please, at least 2 and 3 already left. So okay, so maybe you can find also some names as well. Okay, this is how see that how things are. Okay, but in numbers, so you know, we restrict ourselves very much to be present here, and but of course we provided some people online. So altogether we have about 120 people who followed us. Here you see the bars here, and the 60 online use what we have. It's a kind of tricky because this was only online when we were in COVID time. So we still keep up the same number of people here. We have extremely large number of talks, and I really appreciate all of the efforts that you put into this, and that you use our laboratory. The future depending on you, of course. Go to the VSC Lab webpage, apply with a new project to fulfill the next GPU days in 2024 with the new projects and more interesting results. And be with us. And don't forget, we will have as regularly in October, November, December, the lectures on modern computing, modern scientific computing. This is for you know, beginners to start, and maybe they can join us later in the GPU days. So all in all, we are here and ending the story, and stay tuned, and you can see hopefully some of the talks online in the YouTube, or you can follow us on the GitHub to see the related program codes and everything else. So thank you very much, and I really enjoyed these 2 days with you. It was very interesting. I learned a lot, both from the computing side and from physics and other related fields. So thank you very much, and enjoy, and come back next year. Take care. Okay.
Most már mindenkinek véget vetettek a műsornak.